Hello there, and welcome to Science for Sleep, where curiosity stretches its legs and science takes the slow road toward rest. Tonight, we'll drift together through a question that feels enormous, but quietly personal at the same time. How small are we inside the Milky Way? It's the kind of thought that can make your chest tighten and expand all at once. You might look up at the stars and feel something between awe and uncertainty, a tug between wonder and comfort. But don't worry, we'll take our time with it. Because sometimes, to really understand vastness, you have to start small. Maybe even here, right where you are, with the faint glow of your screen, the quiet around you, and that small awareness inside your mind that is somehow big enough to think about galaxies. Where are you listening from tonight? Maybe you're curled up in bed, maybe it's raining softly outside, or maybe the hum of a late-night city is spilling through the window. Wherever you are, the same sky stretches above you. Even if you can't see it through clouds or light pollution, it's still there. That sprawling ocean of stars, planets, and dark space, reaching farther than any mind can truly hold. Somewhere in that darkness lies our home, not just Earth, but the vast disk of stars we call the Milky Way. And somewhere within that, so small that no telescope could ever single it out, is you, breathing, listening, wondering. If you find this gentle drift through space soothing, or if it helps you unwind while your thoughts slow down, it would mean a lot if you gave the video a like, or subscribed, or simply let it play quietly in the background. It helps this little corner of calm find others who might also be looking for something peaceful to fall asleep to. So, settle in, let your breathing even out, and picture, if you can, the faint shimmer of our galaxy above you. A band of pale light, so familiar, yet so distant in meaning. It's time to take a slow, careful look at where we are in all of this. For most of human history, people didn't even know what the Milky Way was. To the naked eye, it looks like a hazy cloud, a soft stripe of light crossing the night. Ancient cultures gave it different stories. A river of milk spilled by a goddess, a path of souls, a scar left by a celestial fire. Nobody knew they were looking at billions of stars. When you stand outside on a clear night and your eyes adjust, that band across the sky is your edge-on view of our galaxy. We're inside the disk, looking through its densest part like standing inside a glowing fog. It's easy to forget that every faint glimmer there is a sun, and most likely has its own system of planets. Yet from here, it feels small enough to hold in your gaze. We live in a world built to human scale. Roads, trees, rooms, even mountains. They fit roughly within the range of what our senses can handle. The mind adjusts easily to things you can see and touch. But scale in space is different. It's so large that normal comparisons fail. If you try to imagine the distance between Earth and the Moon as a few centimeters, the Sun would have to be several meters away, and the next star would be tens of thousands of kilometers farther. The Milky Way itself would stretch beyond imagination. So when we ask how small we are inside it, we're really asking about proportion, about perspective, and about what it means to occupy a single point in a structure beyond measure. Right now, as you listen, you're sitting on a planet orbiting a medium-sized star in a quiet suburb of our galaxy. The Sun isn't special. It's one of the roughly 400 billion stars in the Milky Way, and most of those are older, larger, or stranger in some way. Around each of them might be planets, rocky worlds, icy bodies, gas giants, some familiar, some impossible. If you picture all of it together, you get a spinning disk of stars roughly 100,000 light-years wide. To cross it at the speed of a light would take longer than human civilization has existed. And somewhere in that colossal expanse, tucked away in a small spiral arm, is us. A few atoms organized briefly into the shape of people, thinking about how small we are. The contrast is dizzying, but it's also grounding in a way, because everything enormous starts from something tiny. The atoms in your body were forged in stars, not poetically but literally. Hydrogen, the simplest element, has been around since the universe began, but the carbon, oxygen, iron, and calcium that make up your blood and bones were born in stellar furnaces, massive stars that lived, burned, and died long before our sun was born. When they exploded, they seeded the galaxy with the ingredients for life. So in a strange sense, being small doesn't separate you from the galaxy. It connects you to it. You are made of it. The Milky Way isn't something far away in the sky. It's inside you, chemically and historically. You are one of its countless tiny echoes. Still, that awareness doesn't quite prepare the mind for scale. The distances between stars are almost empty. Even in the densest parts of the galaxy, they are separated by light years. Our nearest neighbour, Proxima Centauri, is over 4 light years away, about 40 trillion kilometres. That's such a large number, it barely means anything. If the Sun were the size of a small marble, the nearest star would be another marble 4,000 kilometres away. Between them, nothing but darkness and dust, and yet multiply that emptiness by hundreds of billions of stars, and you have the Milky Way, a vast, thin disk of starlight spinning slowly, gracefully around its hidden centre. The centre itself is not a solid thing, but a region, a crowded core packed with stars orbiting a supermassive black hole known as Sagittarius A. It sits about 26,000 light-years from us. In human terms, that's close to forever. If we sent a spacecraft travelling as fast as any we've ever built, it wouldn't arrive for hundreds of millions of years. Still, that invisible heart holds the galaxy together. Its gravity shapes the motions of stars, gas, and dark matter. You could think of it as the Milky Way's anchor, not because it pulls us down, but because it gives the galaxy its coherence. Around that anchor, everything moves in a slow, stately rotation, including our Sun and all its planets. Every 230 million years or so, our solar system completes one orbit around the galactic centre. The last time we were roughly in this position, dinosaurs walked the Earth. Before that, there was no life on land at all. Every moment of life, every generation, every civilization has unfolded during one tiny step of that endless orbit. When you think about it that way, our species hasn't even completed a full lap around our own galaxy. We're still in our first spin, still newcomers, still learning what the night sky even means. From here on Earth, though, everything feels stable. The ground doesn't move, the stars seem fixed, the galaxy looks like a faint smear of light. But in reality, we're all in motion. The Earth is spinning on its axis, orbiting the Sun, and together with the Sun, drifting through space at about 200 kilometers per second. That's fast enough to cross the United States in about 15 seconds. Yet we don't feel it. Space is so empty, and motion so smooth that it's silent. The air doesn't rush past. There is no wind of speed. Just the quiet drift of a planet, a star and a galaxy all spinning in perfect indifference to our sense of stillness. Our place in all of this can seem almost absurdly small. From one angle, it's humbling to the point of insignificance. From another, it's astonishing that something so small can even comprehend the whole. The Milky Way doesn't know we're here. The stars don't adjust their orbits for us. And yet, somehow, on this one little planet, matter has organized itself into consciousness capable of asking, how small are we? That's not nothing. In fact, it might be the most extraordinary thing of all that the universe can, in some small pocket, become aware of its own scale. When astronomers look outward, they use units that stretch the limits of the human mind. A light year isn't just a measure of distance, it's a measure of time. When you look at a star 100 light years away, you're seeing it as it was 100 years ago. The Milky Way itself is so vast that the light from one edge takes 100,000 years to reach the other. So even when we map it, we're looking into the past. The galaxy we see isn't the one that exists right now, but the one as it was before humans existed, before cities, before language. The light that touches your eyes tonight began its journey when mammoths still walk the earth. This strange delay between seeing and knowing is part of what makes the universe feel so surreal. We never see it as it is, only as it was. Even the light from the sun takes 8 minutes to reach us. So when you stand outside and feel sunlight on your face, you're feeling energy released before you took your last 10 breaths. Time and distance merge in space until they're inseparable. To understand how small we are isn't just to think in meters or kilometers, it's to understand that we live inside a vast, slow ocean of time. Still, we can't help but search for scale we can relate to. If you were to shrink the Milky Way down so that it fit inside a dinner plate, the entire solar system would be smaller than a speck of dust floating on that plate. The Earth itself would be microscopic, invisible. And yet, that speck of dust contains everything you've ever known. Every thought, every memory, every love, every story, every piece of music, every dream. The smallness is staggering, but it's not a reason to feel lost. It's a reminder of how much meaning can exist in tiny spaces, how much life and consciousness can arise from so little matter. The Milky Way itself is only one of perhaps 2 trillion galaxies in the observable universe. It's not the largest nor the smallest. It's a fairly average spiral, maybe a bit quieter than most. It contains around 100 billion planets, and at least as many possibilities for life. Somewhere out there, perhaps near another ordinary star, someone might be asking the same question we're asking tonight. How small are we? How vast is the space that holds us? The thought doesn't make the night colder or lonelier. It makes it shared somehow. Every being that looks up at the stars participates in the same act, the act of wondering where they are in it all. When you think about size on this scale, you realize that language struggles to keep up. Words like big and small lose their meaning. They were built for human rooms, not galactic disks. Even numbers start to collapse under their own weight. 1 trillion here, 1 billion there. After a while, they blur into abstraction. So maybe the right way to grasp our smallness isn't through numbers at all, but through feeling. The feeling you get when you look at the sky and realize that what you see is a fraction of what exists. The feeling of being both impossibly small and completely connected to everything at once. You might think that being small in a galaxy this vast would make life meaningless, but in a way it's the opposite. Our smallness gives us clarity. It reminds us that existence doesn't need grandeur to be miraculous. A single neuron firing, a drop of water freezing, a heartbeat continuing. These are cosmic events in miniature. The same physical laws that shape the orbits of stars govern the motion of atoms in your body. The same gravity that keeps planets circling their suns keeps your feet on the floor. The same chemistry that built galaxies built you. Scale is different, but substance is shared. If you could somehow step outside the Milky Way and look back, you'd see a glowing spiral of light, broad, flat, and gently curved. Its arms would wrap around a bright core, fading into darkness at the edges. From a distance it would look still, but every point of light within it would be in motion. Stars orbiting, gas clouds colliding, nebulae giving birth to new suns. It's not a static picture but a living system, vast beyond comprehension, and you're inside it right now, carried along in its rotation without ever feeling the motion. It's quiet, constant, and ancient, and yet it's happening all the time. The Milky Way isn't a backdrop for life, it's part of life. Every heartbeat, every breath, every night sky you've ever seen is connected to it. You're not just inside the galaxy, you are one of its smallest, most temporary expressions. The atoms that make you will someday return to it, scattered, recycled, maybe gathered again in another world. That cycle of transformation, from star to dust to life and back again, has been going on for billions of years, and right now, you're part of it. If you close your eyes and picture the Milky Way not as something distant, but as something you're floating within, it starts to feel a little less abstract. The stars are all around you, above and below, in every direction. The galaxy isn't a thing you look at from outside. It's the space you inhabit, the fabric you're woven into. Even your smallest gestures, your quietest thoughts, your softest breaths. All of them are motions inside the galaxy's vast silent body. You are, in the most literal sense, a piece of it moving within itself. And so we find that the question, how small are we inside the Milky Way, has no single answer. We are small beyond imagining, yes, but we are also inseparable from the thing we're measuring against. We are the galaxy, looking at itself through human eyes. The stars don't know they're stars, the galaxy doesn't know it's spinning, but we do, and that awareness, that faint flicker of understanding, is its own kind of magnitude. When we think about where we are in the Milky Way, it's easy to imagine it as something distant, something far above and beyond our reach. But really our understanding of it began right here on the ground, under the same dark canopy that still stretches over us. Before telescopes, before modern astronomy, before even writing, humans looked up at the night sky and saw not a galaxy, but a neighbourhood. Familiar stars, shapes and patterns repeated through the seasons. Constellations acted like landmarks in an otherwise infinite darkness. They told stories, marked time, and helped guide travel and crops. To them, the stars weren't cold or unreachable. They were companions, reliable and constant, scattered across a dome that seemed to cradle the world. It's strange to think that for most of our species' existence, the Milky Way itself wasn't understood as a galaxy at all. To ancient eyes, it was a cloudy streak, a pale road winding across the sky. It looked so close you could almost imagine walking along it. Even when early thinkers tried to guess its nature, their explanation stayed close to what they could touch. Aristotle thought it was a phenomenon of the upper atmosphere, like lightning or mist. Others imagined it as the glowing breath of celestial creatures, or the light of the sun reflected off the outermost air. The truth that we were seeing billions of distant suns would have been unthinkable to them. But even without knowing the science, they felt the wonder. They knew the sky was vast and that our place in it was small but significant. For people living without city lights, the night sky wasn't a rare sight. It was a constant presence. You would have seen it every night, bright enough to cast shadows. The band of the Milky Way would have been clear from horizon to horizon. Its stars, densely packed, would have shimmered like dust scattered across black velvet. That was the ceiling of their world, and everything they did, from navigating oceans to planting crops, relied on its patterns. The constellations weren't just decoration. They were a calendar, a compass, and a library of cultural memory all at once. Each civilization carved its own meaning into the same set of stars. The Greeks saw gods and heroes, the Chinese saw dragons and palaces, the Maya saw animals and celestial fires. Everyone looked up and saw something familiar, something local, even though they were staring into a galactic ocean. Imagine being one of those early sky watchers, lying on a cool hillside seeing the Milky Way rise overhead. There are no machines, no engines, no noise from roads or cities, only the rustle of the wind and the faint whisper of insects in the dark. The stars are not faint pinpoints as they are through modern haze. They are clear, steady, almost overwhelming. You could spend hours tracing them, watching how they drift slowly westward through the night, how they return night after night in slightly shifted positions. Patterns would reveal themselves, bright clusters like the Pleiades, reddish glows like Antares, a misty smudge that we now call Andromeda. Without realizing it, you would have been looking at another galaxy entirely, the nearest large one to our own, but it would have looked so small that you could cover it with your thumb. In the neighbourhood of night, distance hides itself in plain sight. Our ancestors might not have known what the stars were, but they sensed they mattered. The regularity of the heavens offered comfort. Everything on Earth changed. Seasons, weather, lives. but the stars endured. That stability became a kind of reassurance that the universe itself had order, and in that order, humans began to look for patterns, for relationships, for signs that maybe, somehow, the sky and the earth were connected. They began to measure, to count, to predict. Slowly, curiosity began to turn into science. The sky was no longer just decoration. It was data. When Galileo lifted his telescope to the Milky Way in 1609, he changed that relationship forever. What had always looked like a faint cloud suddenly resolved into countless individual stars. It was a revelation that reshaped the human mind. Those soft white bands weren't vapour or glow. They were distant suns, too many to count. It was the first direct evidence that the universe was far bigger than anyone had imagined. What looked like a neighbourhood was in truth a metropolis without end. Galileo's sketches from that time show him trying to capture what he saw. Clusters so dense they looked like spilled salt. But even his telescope could only reveal a small fraction of what was really there. Today we know that when you look up at the Milky Way, you're seeing only a thin cross-section of one spiral arm. Our solar system sits inside a region called the Orion Arm, a modest spur tucked between two of the galaxy's major arms. When you gaze into that glowing river of stars, you're looking along the length of this arm, through layers of gas, dust and light. It's like looking through fog at night. You can see the lights of nearby houses, but not the shape of the whole city. The rest of the galaxy stretches far beyond what our eyes can grasp. It wraps around us in every direction, but our view is blocked by the very matter that makes it. We're inside the glow, looking out from within it. That's part of what makes this neighbourhood so deceptive. The distances are enormous, but the sky compresses them into a flat surface. Two stars that look side by side might actually be hundreds of light years apart. The patterns we see, Orion, Cassiopeia, the Big Dipper, are coincidences of perspective. They exist only from our vantage point. Move a few hundred light years in any direction, and those constellations would fall apart into random scattering. The sky we call home is an illusion shaped by where we happen to stand. Yet it's an illusion that unites us. Every culture, every person who's ever lived has looked up at that same dome and seen their own reflection in it. That shared illusion became a bridge between imagination and the universe. There's something comforting in the thought that the light reaching your eyes tonight left its source long before you were born. Some of those photons have been travelling for hundreds or even thousands of years. They've crossed vast regions of space to land gently on your retina for an instant, only to vanish again. Each night sky is a mosaic of ages. Some stars died long ago, but their light is still en route, their messages still arriving. Others are just beginning to form, hidden in clouds of dust so thick that even the best telescopes can't yet see them. The neighbourhood of night is alive with motion and change, even though it looks still. What we think of as night is really the side of Earth turned away from the sun, our planet's shadow, stretching out into space. That shadow gives us the chance to look outward. The stars are always there, even at noon, but daylight blinds us to them. When the sun dips below the horizon, we're allowed a glimpse of the rest of the universe. The neighbourhood of night is like a window that opens every evening. Through it, we see a fraction of the Milky Way, our galactic city. We live in one of its quieter districts, away from the dense chaos of the core in a region that's calm and relatively stable. That quiet might be what made life here possible. In the crowded centre, radiation and gravitational forces would have made our kind of existence far less likely. So in a sense, we owe our calm nights to the galaxy's suburbs. If you were to step back far beyond our solar system, the familiar constellations would vanish, but new patterns would emerge. The sun would fade into obscurity, another dim point among billions. Earth would disappear entirely. From that vantage, our planet wouldn't even reflect enough light to be seen. Our entire neighbourhood, every star you can see with your eyes, would fit into a tiny patch of sky smaller than your fingernail. That's how local the visible universe is to us. The rest stretches far beyond what we can ever see without instruments. Yet that small patch of familiar light carries everything that shaped human culture, history and meaning. The night sky we see is both the smallest and most personal part of the galaxy. Even with modern telescopes, mapping our galactic surroundings isn't easy. The dust that fills the plane of the Milky Way blocks visible light. Astronomers have had to use radio waves and infrared imaging to peer through it. Over time, those efforts have built a rough map of our galactic home. It's not perfect, more like a sketch made from inside a fog, but it shows a spiral structure with a bright bulge at the centre and long arms sweeping outward. We can now place our sun roughly halfway between the core and the outer edge, orbiting peacefully in a thin disk. But every time we improve our instruments, we discover more. The galaxy is filled with streams of stars, invisible clouds, and faint trails of ancient collisions. It's more dynamic than we once thought, more alive, more intricate. The more we learn, the stranger and more beautiful the neighbourhood becomes. We've found regions where stars are still forming, enormous nurseries of gas and dust glowing faintly in infrared light. We've found clusters of ancient stars, globular groups that orbit the galaxy's outskirts like satellites, survivors from its earliest days. We've even found evidence that the Milky Way has consumed smaller galaxies in the past, their remnants scattered across the sky like faint fingerprints. The space around us isn't empty or static. It's shaped by billions of years of motion, collision, and renewal. Our neighbourhood, quiet as it seems, is the product of an ancient, ongoing story written in starlight. When you look at the night sky, you're seeing that story mid-sentence. Every pinpoint is a chapter in progress. Stars being born, shining, dying, and seeding the next generation. Even the darkness between them has structure. The black gaps are filled with cold hydrogen clouds, filaments of dust and invisible dark matter that bends light as it passes. To the eye, it looks like emptiness. To the universe, it's architecture. The Milky Way's disk is woven from these unseen threads, its spiral arms tracing the paths of density where stars cluster together. What you see as a faint glow overhead is actually the combined light of hundreds of billions of suns filtered through that cosmic fabric. It's tempting to think of the galaxy as something separate from us, something to be explored and mapped like a new land. But in truth, we're not standing outside it looking in. We are inside it, made of it, carried by it. The starlight you see has travelled across the same gravitational field that holds you to the Earth. The energy that fuels your body is the same kind that burns in stars. When you breathe, you're recycling atoms that once drifted between suns. The neighbourhood of night isn't just above you, it's within you. Every person who has ever lived has shared the same material history, the same galactic origin. That connection makes the scale of the Milky Way feel less isolating and more like belonging. Even so, the mind keeps trying to measure. How far? How big? How many? We can say that the Milky Way is about 100,000 light-years across and 1,000 light-years thick. We can estimate its mass, count its stars, trace its arms. But those numbers don't quite capture the experience of standing beneath it. They don't explain the quiet pull it has on us. For that, you have to feel it. The way the sky expands the longer you look. The way your thoughts slow as the stars come into focus. The neighbourhood of night has always had that effect. It stretches perception until what felt solid and immediate starts to dissolve into something larger. You might notice how different the night feels in different places. In cities, it's subdued, washed out by artificial light. In the countryside, it becomes deeper, more textured. Far from any glow, you can see not only the Milky Way but its structure, its dark lanes, its dense centre, its delicate edges fading into black. Under that kind of sky, it's easier to sense motion, to feel that you're part of something turning. The planet is rotating, the stars are drifting, and you're anchored in the middle of it all. It's quiet, but it's not still. You can't feel it physically, but the awareness is there, like background music you can almost hear. That awareness has guided human thought for millennia. Every scientific breakthrough about our place in the cosmos began with someone noticing something small in the night. A pattern, a shift, a flicker. The neighbourhood of night is full of such hints. The gentle wobble of a star can reveal the pull of unseen planets. The faint glow at the edge of visibility can mark an entire cluster of suns. Even the dark patches between stars tell stories, of dust clouds so thick they block light, of new stars gestating inside them. The sky is a neighbourhood of motion and potential, and we're only just beginning to learn its layout. If you think of the Milky Way as a city of stars, our sun would be a house on a quiet street, and the night sky would be the view from the window. The nearest streetlights are the nearby stars, familiar and bright. Beyond them, the distant glow of downtown, the dense central bulge, glimmers faintly on the horizon, and stretching around it all the faint haze of other districts and suburbs, each with their own lights and rhythms. The city never sleeps. It turns endlessly, new lights flickering on as the old ones fade. From our window we see only a few blocks, but we can sense the rest. The unseen neighbourhoods, the quiet lives unfolding in other corners of the galactic city. Somewhere in that city, perhaps around another star, someone else might be looking up and wondering about their own sky. They'd see the same Milky Way, but from a different angle, a different arm. To them, our sun might be one of those faint anonymous points in the distance. They might not even notice it. And yet, in that symmetry, there's something deeply grounding. We're not central, but we're part of the same neighbourhood. The same rules of physics, the same cycles of birth and decay, the same quiet beauty. The night sky is our connection to all of it. It's not just decoration or backdrop, it's the visual edge of a vast structure we inhabit but rarely think about. When you look at the Milky Way, you're seeing the edge of our home, the thin, luminous boundary between what we know and what we don't. It's not beyond reach, it's where we already are. And as we move slowly onward, the view will change, not tonight or tomorrow, but across the span of ages as our solar system drifts through the galactic sea. The neighbourhood of night will always be here, but its stars will shift, its patterns will evolve, its light will tell new stories. We'll keep looking, keep learning, keep finding meaning in the distance. Because even though the Milky Way is enormous and ancient, the view we have of it, this familiar neighbourhood of stars, belongs entirely to this moment in its history. It's temporary, like us, and somehow that makes it all the more beautiful. When we pull our gaze back from the stars and let our focus return to the ground beneath us, it's easy to forget that our world is part of that same expanse we've been imagining. Earth feels separate, self-contained, like a place apart from the galaxy. We measure our days by sunrises, not by the slow drift of the solar system through the Milky Way. But in truth, every familiar sound and colour, every breath and heartbeat, exists within that vast field of starlight. Our planet may feel like the centre of everything, but it is only a small island in a sea of light stretching far beyond the horizon of thought. If you could see Earth from space, from a distance great enough to take in its whole shape, the first thing you'd notice is how bright it looks. The atmosphere scatters sunlight into a soft halo that makes the planet shimmer like a marble suspended in black water. From the surface, that brightness hides the rest of the universe, but from orbit the contrast is clear. The blue oceans reflect light like mirrors. The continents glow with the pale warmth of deserts and forests. Even the night side isn't entirely dark. Lightning flashes in clouds and human cities glitter faintly like artificial constellations. It's a fragile kind of brilliance, easy to miss from far away, but unmistakable once you know it's there. That small world has a scale that feels comfortable to us. We can circle it in airplanes, cross it in ships, photograph it from above. It has edges, boundaries, and familiar rhythms. The tides come and go, the seasons return. Even the slow motion of continents over millions of years feels orderly when seen from a planetary perspective. But step outside the Earth's orbit, and everything that once seemed vast begins to shrink. Our oceans become streaks of colour. Our mountains flatten into texture. The very air that keeps us alive thins to nothing, and beyond that thin shell the light begins to change. The farther you move from Earth, the less the sun floods everything. The glow fades, shadows deepen. The blackness thickens into something almost tangible. Out there, space doesn't look like it does in pictures. There are no coloured lights or glowing streaks unless your camera lens collects light for minutes or hours. To the eye, it's mostly darkness. The stars are sharp and still, their light unblinking because there's no air to make them shimmer. The sun is still there, but smaller and harsher, its brilliance unsoftened by atmosphere. Every object reflects it in pure contrast, blindingly bright on one side, black as coal on the other. In that hard illumination, Earth itself would look delicate, vulnerable, almost too small to hold everything it carries. The thought can make you quiet for a while. The first people who saw Earth from orbit described a kind of awe they couldn't put into words. Astronauts on early missions said it changed them to see the planet whole, to realise how thin the atmosphere was, how isolated we really are. From space, there are no borders or boundaries. The planet looks peaceful, unified, silent. But what struck many of them most was the emptiness around it. Beyond the blue sphere, there was nothing but black. No nearby world, no close star, no visible anchor. Just a small oasis floating alone in a vast desert of light and shadow. Our world orbits a star we call the Sun, which is itself just one of hundreds of billions in our galaxy. The Sun is classified as a G-type main sequence star, which sounds technical, but really just means it's an average middle-aged star, not too big, not too small. It's been burning steadily for about 4.5 billion years and will continue for roughly 5 billion more. To us, it's everything. Without it, there would be no warmth, no energy, no life. Its light drives weather, photosynthesis, and the chemistry of our bodies. It's easy to think of it as unique, but stars like ours are common. The galaxy is filled with them, some smaller and redder, some larger and bluer, all performing the same basic work of turning hydrogen into light. That light travels across 93 million miles of space to reach us, taking about 8 minutes. It seems instant, but every sunrise you've ever seen is already a memory from 8 minutes ago. When you look at sunlight reflected on water, you're seeing something that happened in the recent past. A delay so small it feels meaningless, but still a reminder that even here, distance has a quiet say in everything. The warmth you feel on your skin began its journey in the sun's core, where atoms collided under pressures and temperatures we can barely imagine. It took thousands of years for that energy to travel from the centre of the sun to its surface, and then just minutes to reach you. Every ray of light carries that history. If we zoom out a little more, our sun becomes just one bright dot among many. Around it, the planets form a small, intricate system. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and a scattering of smaller bodies beyond. Each follows its own path, bound by gravity's invisible hand. From above, it looks ordered and clean, but in reality the distances between planets are immense. The Moon feels far from Earth, yet you could line up 30 Earths between them. Mars, our next planetary neighbour, is more than 50 million kilometres away at its closest. Neptune, the outermost of the major planets, lies so far that sunlight takes more than 4 hours to reach it. The scale grows quickly beyond comfort. To get a sense of proportion, imagine shrinking the sun down to the size of a large orange. On that scale, Earth would be a small pinhead orbiting about 10 meters away. Jupiter would be the size of a marble nearly 50 meters out. The outer planets would be tiny grains scattered hundreds of meters farther still, and the nearest star, our closest stellar neighbour, would be another orange placed more than 2,000 kilometers away. Between those two oranges would be nothing but emptiness. That is our little neighbourhood in the galaxy, a single star and its family of worlds, floating in the dark with vast distances separating it from the next system. It's remarkable that within such emptiness one planet developed life at all. The conditions had to line up with delicate precision. The right distance from the sun, a protective magnetic field, a balance of water and atmosphere, and enough stability for billions of years. Everything about Earth's habitability is narrow, fragile, and temporary. Yet for all its improbability, it happened. Life appeared, evolved, adapted, and eventually became aware enough to look up and ask questions about where it came from. That awareness is part of what makes our planet special. The universe doesn't seem to have a preference for life. It happens when and where the conditions allow, like a spark in dry grass. But on Earth, that spark became self-reflective. When we look out at the night sky, the sun's light hides the stars during the day, but at night, when the Earth turns away, the view opens again. That same light that sustains us becomes the veil that keeps us from seeing the wider cosmos. Only when we're in darkness do we remember that we're surrounded by light far beyond our own. The sun is one of roughly 100 billion stars in this galactic disk, and almost all of them have their own systems. In that sense, our solar system is ordinary. There are planetary systems older, larger, and more exotic than ours scattered everywhere across the Milky Way. Yet in that ordinariness lies a strange comfort. We are not alone in structure, even if we are in awareness. The idea of smallness often feels humbling, but it can also be clarifying. When you realise how little space Earth takes up in the galaxy, you start to see how interconnected everything is. The same forces that shape distant stars also shaped us. Gravity, radiation, chemistry. They operate everywhere, unbroken, consistent. The hydrogen that burns in the sun's core is the same hydrogen that fuels the stars at the galaxy's edge. The carbon in your cells is identical to the carbon in distant nebulae. Scale doesn't change substance. That continuity, invisible but absolute, ties us to every corner of the Milky Way. It's worth remembering that our planet isn't fixed in place. While the Earth spins around its axis once every 24 hours and orbits the Sun once every year, the Sun itself is also moving, completing a long orbit around the galactic centre roughly every 230 million years. Our solar system is carried along in that vast motion, drifting through space like a bubble in a river current. We're never in the same place twice. Every second we move thousands of kilometers through the galaxy without feeling it. The air stays still, the stars appear motionless, yet the whole solar system is gliding along an invisible path that will never repeat. It's strange to think that even as we sit still, the ground beneath us is rotating, the planet is orbiting, and the sun itself is migrating through the galactic sea. From an outside perspective, we are in constant motion, tracing loops within loops within loops. Each movement is nested within a larger one, all of them governed by the same quiet mathematics of gravity. There's no sense of direction in this scale, no up or down, no north or south, only relative positions. The stars above you tonight are not fixed points. They're travellers too, each following its own orbit around the galactic centre. Over millions of years, the constellations we know will stretch and distort until they're unrecognisable. The sky we find familiar is temporary, just a passing arrangement in an ever-shifting sea. Still, from our small vantage point, that sea looks calm. The sun rises and sets with reliable rhythm. The stars return each night in predictable patterns. The vast complexity of motion resolves into a simple, steady cycle that defines our sense of time. That reliability has shaped how we live, It gave rise to calendars, seasons, and the idea of order in the universe. Yet behind that sense of stability lies constant change. The slow migration of the solar system, the aging of the sun, the evolution of the galaxy itself. Every moment of life on Earth unfolds within that continuous transformation, though we rarely notice it. If you've ever stood outside at night, away from artificial light, and seen the Milky Way arching overhead, you've already witnessed this motion in miniature. The Earth's rotation carries you beneath the galaxy's glowing band, revealing it slowly as the night progresses. It's not the stars that move, but you. You're turning with the planet, and the stars are your reference points. That slow movement connects you to everything else: the spin of the Earth, the orbit around the Sun, the drift through the galaxy. The same physics that keeps the moon circling us keeps the galaxy's stars in their endless paths. The scale changes, but the relationship doesn't. Our little world in this sea of light has always been both fragile and resilient. It's fragile in that it depends on a thin layer of gas and water for survival. It's resilient in that it has persisted through asteroids, ice ages, and extinctions. The same sun that could destroy life with a slight change in brightness has also sustained it for billions of years. The balance is delicate, but somehow it holds. When you step outside and look up, you're standing in the only place we know of that has managed to sustain awareness in a universe otherwise silent. That realization doesn't need to feel lonely. It can feel like belonging to something ongoing, a quiet process of matter becoming conscious of itself. There's an image often shared by astronauts who've seen Earth from far away. They describe it as a small blue light surrounded by blackness. But the blackness isn't truly empty. It's full of photons, dust, and distant stars. From that vantage, you can see the sun's light reflected off the oceans, and if you look farther, you might glimpse the faint outlines of the Milky Way, stretching behind it all. It's a reminder that our planet isn't isolated in nothingness. It's immersed in a sea of energy and motion that extends in every direction. The darkness between stars is not void, but a field of invisible potential. Light crosses it constantly, even if our eyes can't see it. Every beam of sunlight that touches Earth has passed through that ocean. Every starlight reflection, every glimmer of moonlight is part of the same ancient stream. That's what it means to live in a galaxy, to be surrounded by light, both near and distant, always arriving, always leaving. We may feel stationary, but in reality, we're sailing through that light. The galaxy around us isn't static. It breathes, rotates, evolves. Our little world is just one mote of dust caught in that slow, graceful movement. If you think about it long enough, it becomes clear that small isn't a weakness here. It's what makes perspective possible. Because we're small, we can see the vastness. Because we're fragile, we recognize the significance of balance. The Milky Way isn't aware of itself, but we are. Every photograph, every measurement, every quiet moment spent looking at the night sky is the galaxy reflecting on itself through human eyes. The realization that we are part of that reflection, that our planet is both tiny and essential to our awareness of the whole, gives scale a different meaning. So when you look up at the night sky and see the faint band of the Milky Way stretching across it, you're not looking outward as much as you think. You're looking through your own neighborhood, across the same field of stars that surrounds you. The light that reaches you is ancient, but it's also local in a cosmic sense. You're in the middle of it, not beneath it. And the little world that seems so separate from that expanse is, in every measurable way, part of the same structure, a particle of awareness floating in a sea of light that never stops moving. When you stand under the night sky and look up at the brightest points of light, it's tempting to think they're all stars, but many of them are not. Some are planets, our familiar neighbours reflecting sunlight back at us across vast distances. They're the other members of our solar family orbiting the same star, moving along paths that never cross, bound by the same gravitational thread that holds Earth in place. We've given them names, sent machines to visit them and study their faces through telescopes, but they remain distant friends, close enough to see, far enough to never touch directly. Understanding how far they really are stretches the mind more than the eye. The nearest of these companions is the moon. It feels close, immediate, something you can point to and imagine reaching with a single leap. Its presence shapes tides, stabilizes the Earth's rotation, and lights the night with a familiar glow. Yet the moon is nearly 400,000 kilometers away. It takes light just over a second to travel that gap. When you look at it, you're seeing it as it was 1 second ago. It doesn't sound like much, but the scale of that distance is enormous compared to what we know instinctively. If the Earth were a basketball, the moon would be a tennis ball about 7 meters away. Between them would be empty space. No air, no sound, just the cold silence of vacuum. The first humans who travelled there in the late 1960s described looking back at Earth as both beautiful and unsettling. The planet hung in space, small enough to cover with a thumb, bright and fragile against the black. The journey took 3 days in a spacecraft moving faster than any vehicle had before. Even then, it was like crossing an ocean without landmarks. The moon may be the closest world to us, but it's already far beyond any sense of nearness we experience in daily life. That distance is why it feels both intimate and unreachable. Beyond the moon lies a space so wide and empty that even our imagination falters. The next planet inward, Venus, comes as close as 40 million kilometers at its nearest approach. The next one outward, Mars, can be about 55 million kilometers away when our orbits align favorably. When you hear numbers like that, they tend to lose meaning, so it can help to think of light, which travels at nearly 300,000 kilometers per second. Light from Mars, even when it's closest, still takes about 3 minutes to reach Earth. When we send signals to spacecraft there, it's like sending messages to the past. By the time a rover receives a command, the Earth has already moved on. This delay turns the planets into echoes rather than conversations. We see them not as they are, but as they were minutes ago, sometimes hours. The farther out we look, the longer the gap becomes. It's a strange way to think about our solar system, not as a collection of objects existing together in the present, but as a series of time-shifted moments all unfolding at once. The Sun itself is 8 minutes behind us. Jupiter, depending on its orbit, can be between 30 and 50 light minutes away. Neptune sits 4 light hours from Earth. When you imagine these distances, the familiar warmth of our neighbourhood starts to fade into abstraction. And yet, despite the scale, we still call them our neighbours. Maybe because we can see them, or because they orbit the same star. The word neighbour makes the vastness feel smaller, manageable. It gives shape to what would otherwise be impossible to grasp. For thousands of years, those distant points of light were the only other worlds we knew. Early astronomers watched them wander against the fixed background of stars and called them planets, from the Greek word for wanderers. They didn't know what they were, only that they moved differently. It took centuries of observation to understand that these wanderers were other worlds, reflecting sunlight just like our own. Mercury, the smallest and fastest, hugs the sun so closely that it's rarely visible except at dawn or dusk. Venus, wrapped in clouds, shines brightest in the night sky, sometimes mistaken for a star about to burst into flame. Mars glows with a reddish hue, a tiny ember drifting among the constellations. Jupiter and Saturn move more slowly, their brightness steady, their orbits long and grand. Through a telescope, Jupiter shows stripes and swirling storms. Saturn reveals its rings, thin bands of ice and dust spread across hundreds of thousands of kilometers. These sights, once invisible to the naked eye, transformed our understanding of what lies beyond Earth. When Galileo first turned his telescope toward Jupiter, he discovered 4 small points of light near it that changed position night after night. They weren't stars, but moons orbiting the planet. It was the first clear evidence that not everything revolved around Earth. That discovery expanded our sense of place in the universe more than any map ever could. It showed that the heavens were not a fixed dome, but a system, dynamic, interconnected, and vast. Each new discovery since then has added another layer of scale, each one reminding us how small our own orbit really is. If we step farther out, the planets become less like companions and more like distant cities, connected only by faint radio signals. The Voyager spacecraft, launched in 1977, are still travelling outward through the solar system. They have passed all the planets and are now moving through interstellar space, beyond the reach of the sun's wind. Each carries a golden record, a small message from humanity to whoever might one day find it. As of now, they are over 23 billion kilometres away. The signals they send take more than 20 hours to reach Earth. Every transmission is a whisper from a traveller already beyond sight, carrying news from a place no human has ever been. That distance changes how we think about connection. On Earth, distance is measured in travel time or effort. Across oceans or continents, we can still imagine bridges, flights, or signals bouncing between satellites. But beyond our atmosphere, distance becomes something else entirely. There are no shortcuts, no highways through the void. Each kilometre is empty, silent, and absolute. Space is not a medium we move through. It's the absence of everything that could help us cross it. The only reason we can even sense the planets is because of light, the one thing that can traverse the gulf between worlds. Light is our messenger, our translator, our only connection. It carries information from the sun, from the planets, from the stars. It tells us what's there, even when we can never go. When a telescope captures light from Saturn's rings, it's catching photons that left the sun more than an hour ago, bounced off the ice, and travelled back across 1 billion kilometres to reach us. That journey happens constantly everywhere, forming a quiet web of communication across the solar system. The light carries stories, the chemistry of atmospheres, the temperature of surfaces, the presence of clouds and storms. Without it, the planets would be invisible. It's easy to forget that what we see when we look at the planets is reflected sunlight. They don't shine on their own. Every glimmer from Venus or Mars is borrowed. The sun illuminates them, and they return a fraction of that light toward us. In a sense, the solar system is a hall of mirrors, each world reflecting the same source from different angles. The brightness of each planet depends on its distance, size, and how its surface or atmosphere scatters light. That's why Venus looks so brilliant. Its thick clouds reflect most of the sunlight that hits them. Mars, with its dark, rusted soil, absorbs more and shines less. Through observation, we've learned that each of these worlds has its own personality, though none are quite like ours. Mercury is a scorched stone where day and night temperatures swing from blistering heat to deadly cold. Venus, beneath its soft glow, is a furnace wrapped in clouds of sulfuric acid. Mars, dry and dusty, once had rivers and lakes but lost them long ago. Jupiter is a storm in motion, its great red spot a hurricane larger than Earth. Saturn, with its rings, is elegant and cold, its moons scattered like jewels. Uranus and Neptune are pale blue spheres of gas and ice, spinning far from the sun's warmth. Together they make up our local family. 8 major planets, dozens of moons, countless asteroids and comets, all orbiting the same star in patterns older than civilization. When you compare their sizes, Earth begins to look modest. Jupiter could fit more than 1,000 Earths inside it. The Sun could swallow 1 million. And yet that very modesty is what allows our planet to exist as it does, stable, temperate, balanced between extremes. From far away, it's hard to imagine that such a small world could host oceans, forests, and cities. But size doesn't dictate significance. Our place among these planets is defined not by scale, but by conditions. The narrow band where water can exist as a liquid, where temperatures allow life to thrive. That thin zone, just right for complexity, is what makes our little world rare. If you could look at the solar system from above, you'd see the planets moving along their paths like clockwork, each tracing its own orbit around the Sun. The inner planets move faster, the outer ones slower, each maintaining perfect balance through gravity's pull. The scale is hard to imagine, yet the precision is absolute. This pattern has held for billions of years, long before life began on Earth. Every orbit, every rotation, every eclipse follows the same laws, the same rhythm. To us, it looks still, but it's a constant motion, a slow dance of mass and distance that defines our existence. The distances between these familiar friends remind us that isolation and connection coexist in space. Each planet follows its own path, never crossing another's, yet all a part of the same system. Their gravity affects one another, their histories are intertwined. Comets that pass near Jupiter can be flung inward toward the Sun, or outward toward the edges of the solar system. Asteroids in the belt between Mars and Jupiter are held in place by delicate gravitational balances. Nothing in space is truly alone, even when separated by billions of kilometers. Everything is linked by the invisible geometry of motion. As technology has improved, we've reached farther into this neighborhood. Spacecraft have orbited every major planet, and robotic probes have landed on several. Cameras have captured images of alien skies, a blue sunset on Mars, a methane rainstorm on Titan, lightning flashing inside Jupiter's clouds. Each photograph is a message from another world, a postcard sent across millions of kilometers. When we receive them, we're reminded that our solar system isn't static. It's alive, changing, full of weather, wind, and motion. It's easy to think of space as silent, but these planets are anything but still. Even so, the vastness between them makes every image, every bit of data, a small miracle. When a signal from Neptune reaches Earth, it has travelled for hours, weakened by distance, distorted by cosmic radiation, and yet it arrives, carrying the imprint of a world billions of kilometers away. That thin thread of communication across space is fragile but steady. It's a testament to how far curiosity can reach. We can't visit most of these places in person, not yet, but we can know them. We can measure their temperatures, map their storms, and imagine their landscapes. That act of knowing, of bridging distance through observation, is how we make distant friends familiar. And while the planets feel remote, the distances between stars make them seem almost close. The nearest star system to us, Proxima Centauri, is over 4 light-years away. If you converted that into kilometers, it would be about 40 trillion. Even if we could travel as fast as the Voyager probes, it would take more than 70,000 years to reach it. That's the true scale of our neighborhood, a handful of small worlds orbiting one star, with the next star so far away it might as well be another universe. Within that gap lies the essence of cosmic distance. It's not just far, it's beyond our physical reach for now. Still, that separation doesn't diminish our connection. The light from those distant stars still reaches us. Their gravity still affects the galaxy's overall motion. Their existence shapes the Milky Way as much as ours does, even if we'll never meet. The space between them isn't emptiness so much as a medium of potential, a place where dust and gas drift, where comets wander, where the faint traces of cosmic rays whisper through. Between every world and every star lies the fabric of the galaxy itself, invisible but constant, carrying light, matter, and motion through its depths. When you think of the solar system in this way, it stops being a set of isolated worlds and becomes part of a continuous whole. The sun's light connects them, gravity binds them, and motion carries them together through the galaxy. Each planet, no matter how distant, shares the same journey. They orbit the same center, move through the same spiral arm, and drift together through interstellar space. Our little group of worlds is a single thread in the larger pattern of the Milky Way, a small but complete ecosystem of matter and light. The distance to these familiar friends, vast as it is also what gives them beauty. It allows them to exist independently, each with its own weather, colours and character. It gives us perspective, a sense of how large the universe must be if even our nearest companions are separated by millions of kilometres. And yet, despite that scale, we can still point to them, still see their glimmer in the night sky, still call them by name. Distance, it turns out, doesn't erase familiarity, it deepens it. Once we move past the orbit of Neptune, the light begins to thin. The warmth that sustains life on Earth fades until it's little more than a memory. Beyond the planets, the sun no longer dominates the sky. It becomes a bright, hard point of light, not much different from the stars that surround it. Out here, the familiar world of orbits and atmospheres gives way to something quieter. Space feels different, emptier, but also strangely open, as if you've crossed an invisible line between the solar system we know and the galaxy that contains it. This region isn't entirely empty. The outer reaches of our system are filled with debris, ice, dust, and the remnants of formation. These are the leftovers from when the sun and planets first came together, billions of years ago. Most of the material that didn't form into planets was pushed outward by radiation and gravity, collecting into vast, thin regions that stretch for unimaginable distances. The first of these regions is known as the Kuiper Belt. It begins just beyond Neptune and extends outward for billions of kilometres. It's a quiet zone, a place of frozen worlds that rarely see sunlight, orbiting slowly, almost forgotten. Among those distant bodies are Pluto, Eris, Haumea, Makemake, and others. The dwarf planets. They are small, cold, and dim, yet each one carries traces of the early solar system's history. Pluto, once considered the 9th planet, was reclassified after astronomers realised it was just one of many similar objects out there. Its discovery in 1930 was an accident of careful observation, a faint moving dot captured on photographic plates. Even then, it was clear how remote it was. Sunlight there is 1,000 times weaker than on Earth. A day lasts just over 6 of our days, and a year stretches on for more than 2 centuries. When you imagine standing on Pluto, the sun would appear no larger than a bright star. The darkness would feel almost physical. The spacecraft New Horizons reached Pluto in 2015, after travelling for nearly a decade through the void. When it arrived, it sent back images that surprised everyone. A world of mountains made of ice, plains of nitrogen, and faint hazes in its thin atmosphere. It wasn't a dead rock, but a place still active in its own slow, frozen way. After passing Pluto, New Horizons kept going. It's still moving outward, exploring the Kuiper Belt, where countless icy objects orbit in silence. Each one tells a story about the earliest days of our solar system, when dust and gas first gathered under gravity's pull. As you travel farther, the sun's warmth fades completely. The solar wind, the stream of charged particles flowing outward from the sun, begins to weaken. Eventually you reach a boundary where that wind stops pushing against the interstellar medium, the thin gas and radiation that fill the space between stars. This is the edge of the sun's influence, called the heliopause. Beyond it, the galaxy itself takes over. The space past this point isn't part of the solar system anymore. It belongs to the Milky Way. The Voyager spacecraft crossed this boundary years ago. When they did, their instruments detected the change. The solar wind disappeared, replaced by the faint hum of interstellar particles. They are now farther from Earth than any human-made object has ever been, drifting outward with no destination, carrying a record of our existence. What lies beyond that boundary is difficult to describe. The darkness becomes more complete, yet it's not empty. Between the stars lies a thin mist of atoms and dust, the interstellar medium. It's incredibly sparse, with only a few atoms per cubic centimetre, but across the vastness of space, it adds up. This material is the raw substance from which new stars and planets will one day form. In it float the remnants of old stars, blown apart in explosions long past. Tiny grains of carbon and ice drift through that darkness, carrying traces of chemistry older than our solar system. If you could drift there yourself, you wouldn't see much. The stars would look sharper, their light undistorted by atmosphere. The Milky Way would stretch across the sky like a vast pale band. You'd feel no wind, no sound, no sense of up or down. The silence would be absolute. It's a kind of emptiness that defies intuition. Not void, but presence spread so thin that it becomes invisible. Out here, the familiar cues of warmth and light no longer apply. The only constant is motion, the slow, steady drift of everything around the galactic centre. Distances in this region become hard to measure in the way we're used to. The Kuiper belt ends around 50 astronomical units from the Sun. That's 50 times the distance between Earth and the Sun. But even that is only the beginning. Beyond it lies a vast spherical region called the Oort cloud, a swarm of icy bodies stretching perhaps up to 100,000 astronomical units. This is where comets are born. Occasionally, one is nudged inward by a passing star or the pull of the galaxy's tides, beginning a long fall toward the inner solar system. When it approaches the Sun, its ice vaporizes, forming the glowing tails we see from Earth. Most of the time, though, these objects remain frozen in the deep dark, orbiting quietly for billions of years. The Oort cloud is so distant that no spacecraft has ever come close to it. It's mostly theoretical, inferred from the behavior of comets. If you could stand on one of its icy bodies, the Sun would be little more than a bright speck. The nearest stars would seem just as bright, and the boundary between our solar system and the galaxy would blur. Out there, the idea of a home system starts to lose meaning. Gravity still binds those objects to the Sun, but only faintly. The pull of other stars, or even the general mass of the Milky Way, can tug them away over time. The edge of our solar system isn't a wall, but a gradual fading, a transition from the domain of one star to the shared gravity of many. The darkness that fills this space isn't something sinister. It's simply the absence of concentrated light. The energy here is diffuse, spread across unimaginable volumes. Yet even in that darkness, there's a subtle glow. Every star in the galaxy contributes to it. Faint, overlapping light that fills space with a kind of background brightness. If your eyes were sensitive enough, you'd see that glow as a soft haze like distant fog. It's the combined output of hundreds of billions of stars, too faint individually to see, but together forming a quiet ocean of light. That glow is what we call the Milky Way when we see it from Earth. From within, it's like being inside a vast luminous cloud. It's easy to think of the galaxy as a collection of points, stars, planets, nebulae, but it's more like a gradient. The density of stars and gas increases toward the centre and fades toward the edges. We live in one of the thinner, quieter regions. Beyond the Oort cloud, the stars begin to feel closer again, not because they are, but because the Sun's dominance has faded. We're no longer in a solar system, we're in the galactic field. Space here belongs equally to every nearby star, gravity from the Sun, from Alpha Centauri, from the galactic core. All of it mixes into one slow, combined influence. The darkness deepens, but it also becomes communal, a shared medium that connects everything. If you were to continue travelling outward, you would eventually pass close to other stars, though close in galactic terms still means light years apart. The nearest system, Proxima Centauri, lies just over 4 light years away. Between us and it, there's nothing solid. No dust clouds dense enough to see, no stray planets in sight. Just thin gas, occasional particles, and the invisible structure of magnetic fields. Yet through that emptiness, light still travels. It crosses the distance unimpeded, bringing with it the stories of both worlds. Every photon that leaves the sun travels outward forever, unless it's absorbed by something along the way. Most will drift through this deep darkness until they're lost in the general light of the galaxy. It's strange to think that space, which looks so silent and still, is actually dynamic. The interstellar medium isn't static. It moves, ripples, and interacts. Shock waves from distant supernovae pass through it, compressing clouds of gas that may one day form new stars. Magnetic fields twist and guide charged particles through it. Even cosmic rays, high-energy particles from across the universe, stream through this darkness constantly, unseen but real. Everything, even emptiness, has structure. It's just stretched so thin that only our instruments can detect it. For a long time, humanity imagined the solar system as the whole of the universe. The idea that there could be other stars, other galaxies, was beyond reach. Even when telescopes improved, the scale of what lay beyond the planets seemed too great to grasp. But as we pushed farther outward, with machines, with mathematics, with imagination, the boundaries expanded. What once felt infinite became a small part of something larger. The farther we go, the more we realize that there may be no clear edge at all, only a continuous unfolding of scale. As you drift mentally beyond the last known objects of our solar system, the sun behind you fades into the general starlight. Ahead lies the rest of the galaxy, a vast disk of stars stretching for 100,000 light years. From this vantage, the idea of beyond becomes relative. You haven't left anything behind, you've simply joined a broader field. The darkness around you isn't isolation, it's inclusion on a larger scale. Every point of light in that field is a star, most with its own planets, perhaps its own inhabitants wandering about their own boundaries. The deep space beyond the planets is a place of extremes. Temperatures drop to just a few degrees above absolute zero. Radiation from distant stars becomes the only source of energy, yet it's not lifeless in the sense of being without purpose. It's a kind of quiet workshop where new things begin. The dust drifting here will, over millions of years, collect into clouds dense enough to collapse under their own gravity. Those clouds will ignite, forming new stars. Around those stars, new planets will form, repeating the process that once shaped our own system. The darkness we imagine as emptiness is actually the galaxy's fertile ground, waiting for the next cycle of creation. If you could see it all at once, the sun behind you, the faint outlines of other stars ahead, the invisible filaments of gas connecting them, it would feel like standing in the middle of something enormous and alive. Every direction would look the same, filled with faint light, faint motion, faint potential. The concept of beyond would stop making sense, because there would always be more. The space between stars isn't a border, it's the substance of the galaxy itself. Out here, even time feels different. Without landmarks or rotation, without sunrise or sunset, it becomes harder to measure. Seconds and hours lose meaning. You might mark time by the pulse of distant radio signals from pulsars, or by the slow drift of stars relative to one another. Everything moves, but so slowly that from a human perspective it feels still. The stars we see tonight will have shifted only slightly in 10,000 years. On this scale, change is geological, evolutionary, almost imperceptible. The darkness deepens not only in distance but in time, and yet, even in this vast quiet, the familiar is never completely lost. The sun's light, though faint, still travels outward, a bubble expanding through space. Within that faint glow, traces of our presence exist. Radio waves from early broadcasts, signals from spacecraft, radar pulses. They move outward at the speed of light, spreading through the galaxy. Most will fade into the background noise, but for a while, they mark the existence of a small, curious species orbiting a yellow star. Our voice, in a sense, continues into the darkness long after we stop speaking. It's comforting to think that even in the deepest parts of space, something of us remains connected. Every planet, every comet, every grain of dust that originated in the solar system carries a trace of the sun's warmth. They all share the same origin, the same light, even as they drift apart. The farther they go, the more they become part of the galaxy itself. The edge of the solar system isn't a boundary of exclusion, but of merging, a place where our little system dissolves into the greater fabric of the Milky Way. From this perspective, the darkness doesn't feel empty anymore. It feels like a continuation, a gentle blending of one kind of order into another. The light of the sun fades, but the light of other stars replaces it. The gravity that once held planets in neat orbits gives way to the larger pull of the galaxy. The transition is seamless, natural. There's no wall, no edge, no sound of crossing over. Only the gradual awareness that the scale has changed again. What once seemed infinite now feels local, and what lies beyond becomes the new measure of vastness. As we drift deeper into that region, where the last traces of the sun's warmth vanish completely, the darkness becomes an environment of its own. It has texture, temperature, and motion. It carries faint whispers of radiation from the birth of the universe, the cosmic microwave background, a remnant of the Big Bang, filling all of space with a soft, steady glow. Even the deepest darkness holds memory. It contains the past imprinted in light so ancient that it predates stars themselves. In that sense, the farther we move beyond the planets, the closer we get to the origins of everything. In the middle of all that distance and darkness, everything we know still depends on a single star. It's so familiar that we rarely think of it as a star at all. We call it the sun, and it's easy to forget that it's not unique, not rare, not even particularly large. Yet without it, nothing on Earth would exist. Not the oceans, not the air, not life itself. When we look up at it, we're not seeing an object in the sky. We're seeing the furnace that powers our entire world, the core of our local system, the quiet engine that's been burning steadily for more than 4 billion years. If you could see the sun from the same distance you see other stars, it would appear as just another faint point of light among billions. From a planet orbiting a nearby star like Alpha Centauri, it would look unremarkable, a modest yellow glow barely distinguishable from the rest. But from here, up close, it fills our sky, floods our days with light, and defines the rhythm of our lives. Its energy shapes weather, drives wind and rain, and even influences our mood and health. The sun is both ordinary and irreplaceable, one of those contradictions that seem to define the universe. The sun is about 1.4 million kilometers across, more than 100 times wider than Earth, and it contains 99.8% of all the mass in the solar system. Everything else, the planets, moons, asteroids and dust, adds up to almost nothing in comparison. It's a sphere of plasma, not solid but fluid, constantly churning. The temperature at its surface, called the photosphere, is around 5,500 degrees Celsius. That alone is unimaginably hot, but it's nothing compared to its core, where temperatures exceed 15 million degrees. In that central region, hydrogen atoms collide and fuse into helium, releasing energy that slowly works its way outward over thousands of years before escaping as light. Every photon that reaches Earth began as that slow chain of reactions deep inside the sun's heart. When that light finally leaves the surface, it travels through space at the speed of the light, reaching Earth 8 minutes later. It arrives as a constant stream of energy, enough to sustain every living thing, drive photosynthesis, and keep our planet's surface warm enough for liquid water. The sun is, in every practical sense, our only source of power. Even the energy stored in fossil fuels or wind or waves originates there. Every plant that grows, every storm that forms, every current in the ocean owes its motion to the heat and light of the sun. It is, quite literally, the reason anything moves at all. And yet, for all its dominance, the sun is stable in a way that few things in the universe are. It doesn't flicker or pulse noticeably, doesn't vary much in brightness or heat. Its balance is almost perfect. The inward pull of gravity is matched exactly by the outward pressure of fusion. That equilibrium has held for billions of years and will continue to hold for billions more. It's the kind of stability that allows complexity to arise, the steady background against which life can evolve. If the sun were more erratic, brighter one year and dimmer the next, Earth's climate would swing wildly, and our world might never have found balance. The sun's reliability is the quiet foundation of everything. When astronomers study it, they see not a flat disk, but a dynamic, restless surface. Massive loops of plasma arch into space along magnetic lines. Dark spots, cooler regions, appear and vanish in cycles. Streams of charged particles escape into space as the solar wind, flowing outward past the planets and eventually blending into interstellar space. The sun may look calm from a distance, but it's alive with movement. Its outer layers boil like water on a stove, convection cells rising and falling in patterns so large they could swallow continents. Its atmosphere, the corona, extends millions of kilometers outward, invisible except during eclipses when its faint halo of light becomes visible around the moon's shadow. The sun's influence doesn't end with light. Its magnetic field stretches far into space, carried by the solar wind. That field shapes the environments of all the planets, bending and twisting as it interacts with theirs. When solar storms erupt, massive bursts of energy from the sun's surface, they send waves of charged particles across the solar system. When those particles reach Earth, they collide with the magnetic field and atmosphere, creating auroras near the poles. Those shimmering curtains of light are visible reminders that we live under the constant influence of a star. Every flicker in the northern or southern sky is a trace of that connection, a silent conversation between our planet and its parent sun. If you could look inside the sun, you'd find that most of it is hydrogen, with some helium and small traces of heavier elements. In its lifetime so far, it has converted a fraction of that hydrogen into helium through fusion, and in doing so, it's lost a small amount of mass, about 4 million tons every second, turned into energy by Einstein's famous equation. Even at that rate, the sun still has enough fuel to continue burning for roughly another 5 billion years. It's only at the end of that long life that things will change dramatically. When the hydrogen in its core runs low, the balance between pressure and gravity will shift. The sun will begin to expand, becoming a red giant. Its outer layers will swell outward, possibly engulfing Mercury and Venus, and maybe even Earth. Its surface will cool and redden, but its total brightness will increase. After a few 100 million years in that state, it will shed its outer layers entirely, leaving behind a dense, hot core, a white dwarf, surrounded by a faint shell of glowing gas. The sun's light will fade gradually, but the remnants of its matter will persist, drifting through the galaxy, becoming part of something new. The same material that once made life possible on Earth will one day mix into clouds that form new stars and planets. That long future feels distant, but the process is already underway in slow motion. Every second, the sun changes slightly, losing a little mass, shifting its balance, sending new waves of radiation through space. For us, the difference is invisible, but the scale of time makes every moment part of that larger evolution. The star we call home isn't static. It's a living system, aging in the quiet way that stars do. It doesn't need to hurry. It works on a timeline so long that even the rise and fall of civilizations is just an instant in its steady glow. It's remarkable that a sphere of plasma can sustain such order for so long. Stars like the sun are self-regulating. If fusion speeds up and the core gets too hot, pressure increases, causing it to expand slightly, which cools it and slows the reaction. If it cools too much, gravity compresses it, heating it up again. This delicate balance keeps the sun stable, It's a natural thermostat operating on cosmic scales. The laws that govern it are simple: gravity, pressure, temperature. Yet the result is a structure capable of maintaining equilibrium for billions of years. The universe's complexity rests on that kind of stability, not chaos. From Earth, the sun appears to move across the sky each day, rising in the east and setting in the west. But that apparent motion is our own rotation, not the sun's. The sun itself rotates too, but much more slowly. Once every 25 days at its equator, and more slowly near its poles. Its rotation twists its magnetic field over time, building up tension that eventually releases in solar flares and coronal mass ejections. The sun's behaviour follows cycles, roughly every 11 years, during which sunspot activity rises and falls. These cycles affect space weather, radio communication, and even climate patterns on Earth. The connection between our world and our star runs deeper than light alone. Even beyond its physical effects, the sun holds a place in human imagination, unlike anything else in the sky. It's been worshipped, feared, measured, and painted since the beginning of civilization. Every culture has stories about it, gods of light and warmth, myths of rebirth and dawn. Long before we knew it was a star, we sensed its power. It governs the rhythm of life on Earth: sleep, growth, migration, and weather. Every plant leans toward it. Every animal adjusts its cycle to its rising and setting. Even our bodies follow its pattern through circadian rhythms, an ancient biological memory of sunlight. When we finally understood what the sun really was, it didn't diminish its wonder. Knowing that it's a fusion reactor 100 times wider than Earth only deepened the awe. Science didn't make it smaller, it made it more intimate. The light that falls through your window each morning isn't abstract energy. It's the direct result of atoms fusing in the sun's core. It's part of a continuous flow of energy that has connected us to that star since the beginning of life. Every cell in every organism depends on it. The sun's rays drive photosynthesis, which in turn sustains the entire food chain. Even in the deep ocean, where sunlight never reaches, the energy that feeds life originates from processes powered by the sun's influence on Earth's surface. The sun is also our primary clock. Its position in the sky has guided timekeeping for as long as humans have measured time. Sundials, calendars, solstices, and equinoxes all trace back to its motion relative to Earth. The tilt of our planet's axis creates seasons, making sunlight stronger or weaker, longer or shorter through the year. Everything about our perception of time, the sense of days passing, years turning, is tied to how we orbit our star. Without that rhythm, life as we know it would lose structure. The sun gives time meaning by giving it variation. It's strange to think that this everyday light, this ordinary warmth, is the same kind of energy that fills the galaxy. The sun's spectrum of light is broad. Visible rays, infrared heat, ultraviolet radiation, and more. Some of it sustains life, some of it can destroy it. The ozone layer around Earth filters the most harmful rays, while letting through just enough to drive chemistry and warmth. In that balance, again, is the story of survival. Everything we know about life is built on finding equilibrium within the range of what the sun provides. Too little energy, and the planet would freeze. Too much, and it would burn. We exist in the narrow zone where light becomes life. Beyond Earth, the sun continues to shape the planets differently. Mercury is blasted by its heat. Venus, wrapped in thick clouds, traps that heat until its surface becomes hotter than an oven. Mars, too far out, receives less warmth, leaving it cold and dry. Each world's character is defined by how much sunlight it gets, how it retains or loses that heat. Even the gas giants far beyond the warmth of the sun feel its influence. Their upper atmospheres shimmer faintly in ultraviolet light, and their magnetic fields interact with the solar wind. The sun's reach extends across the entire system, defining the boundaries of everything we know. The solar wind that flows from it never truly stops. It continues outward, spreading through space, eventually merging with the interstellar medium. That flow carries with it a record of the sun's activity, its chemical signature, its rhythm, its changes. In a sense, the sun leaves a trail behind it as it moves through the galaxy, a faint wake of particles marking its passage. Everything that orbits it is part of that motion. We too are being carried along through the Milky Way at over 200 kilometers per second, following our star's path around the galactic center. From our perspective, the sun feels stationary. From the galaxy's perspective, it's a traveler, tracing a slow orbit that takes hundreds of millions of years to complete. When we call the sun our star, we're claiming a kind of kinship that goes beyond geography. It's not just the center of our system, it's part of our identity. Every human who has ever lived has depended on its light, measured time by its motion, and found comfort in its warmth. We evolved under its rays, our eyes are tuned to its spectrum, our biology synchronized to its rhythm. It is, quite literally, our environment in the deepest sense. Without it, we wouldn't just be cold, we wouldn't be possible. Even knowing that there are billions of other stars, it's hard not to feel something personal about this one. It's the star that lights our days, the one we see rise and set, the one whose energy pulses in every heartbeat. It connects the smallest details of life to the largest scales of the cosmos. From the fusion of hydrogen atoms to the flowering of plants, it's the same story continuing in different forms. The sun isn't just above us, it's within us, in the carbon, oxygen, and energy that make up our bodies. When you think about it that way, the idea of home expands. It's not just the earth beneath your feet, or even the solar system that surrounds us. It's the star at the center of it all, the constant presence that binds everything together. As our solar system moves through the galaxy, that star carries us with it, its gravity holding us in a fragile balance. We are passengers on its journey, protected by its warmth, powered by its light. When you begin to think about how many stars exist beyond the sun, the numbers start to slip away from ordinary meaning. Our minds are built for counting things we can see or touch. Apples in a bowl, cars on a road, people in a crowd. Even when we stretch that sense into the thousands or millions, it's still something we can picture. But the Milky Way is a place where counting stops working the way we expect. Here, the scale is so vast that the difference between 1 million and 1 billion becomes less a matter of arithmetic and more a matter of surrender. At some point, the brain simply gives up trying to imagine quantity and replaces it with wonder. Astronomers estimate that the Milky Way contains somewhere between 100 and 400 billion stars. The range is wide because no one can see them all directly. The galaxy is thick with dust that blocks our view, and many stars are too faint to detect with current instruments. What we can do is count a small patch of the sky, measure how many stars appear there, and then multiply by the number of similar patches that would fill the galaxy's volume. It's an approximation, but even the lowest estimates are staggering. Every point of light you see on a clear night is just one drop in a cosmic ocean so deep that even light takes tens of thousands of years to cross it. When you look up at the sky without a telescope, you can see only about 5,000 stars with the naked eye under perfect conditions. Half of those are below the horizon at any given time, so in one view, you might see 2,000 or 3,000 at most. It's an impressive sight, but it's barely anything. In a galaxy of hundreds of billions, that's less than a fraction of a percent. The night sky looks crowded, but it's almost empty compared to what's really there. The visible stars are just the nearest and brightest, our immediate neighbours in the galactic neighbourhood. Beyond them, the density increases invisibly, each distant star adding to the collective glow that forms the Milky Way's band across the sky. When early astronomers tried to count the stars, they ran into this problem quickly. Even with telescopes, the number grew too large, and the instruments too limited. Each increase in magnification revealed more stars behind the ones already seen. as if the sky had no end. The deeper they looked, the more it seemed that the universe had no edges. Today, we can use automated surveys, powerful detectors and computers to map vast sections of the galaxy. But the truth remains the same. The more precisely we count, the more countless it becomes. Every advance in technology expands the total rather than finishing the task. The galaxy seems to grow with our curiosity. It's not just the number of stars that's hard to imagine, it's their diversity. They come in all sizes, colours and lifespans. Most are smaller and dimmer than the sun, tiny red dwarfs that burn slowly for trillions of years. Others are massive and short-lived, shining so brightly that they use up their fuel in a few million years before collapsing or exploding. Between those extremes lies every possible variation: white, yellow, orange, blue, each with its own temperature, mass and character. Our star, so familiar to us, sits somewhere in the middle. It's not exceptional, just stable and comfortable, part of the quiet majority that holds the galaxy together. When you look at the Milky Way in the night sky, you're seeing this collection of stars as a single band of light. The human eye can't distinguish individual points at that density. What appears as a smooth glow is actually billions of distant suns layered along the plane of our galaxy. Through a telescope, that hazy strip resolves into countless dots, each a separate world. Galileo was the first to describe this in detail. When he turned his small telescope toward the Milky Way, he wrote that it was nothing but a congeries of innumerable stars. The word innumerable captures something important, not just quantity, but the recognition that the mind reaches a limit. There comes a point where numbers stop representing reality and start standing in for awe. If we could somehow see all the stars at once, the sky would never be dark. Every direction would shine. But most of those stars are too far, their light too faint, their energy scattered by dust and distance. That darkness we see between them isn't the absence of light, but the sum of too much light spread too thin. The universe is full, not empty, but it's full in a way that overwhelms rather than illuminates. The fact that we see darkness at all is a result of time and distance. Light takes time to travel, and space expands faster than light can fill it completely. We live in the balance between enough light to see and enough distance to leave room for shadow. When scientists measure the number of stars, they don't count individually. They measure mass. They know roughly how much matter the galaxy contains and how much of that mass is in stars. By dividing the total by the average stellar mass, they estimate the number. It's like weighing a forest instead of counting the trees. The result gives us a sense of scale, but not a picture we can hold. If we tried to count each star one by one, even at 1 star per second, it would take more than 10,000 years to finish. And by the time we were done, new stars would have formed and old ones would have died. The galaxy doesn't wait for us to keep up. Among those billions of stars, many are bound together in systems. Roughly half of all stars are part of binary or multiple systems, where 2 or more stars orbit each other. Some dance in pairs, others in clusters of dozens or hundreds. These systems form patterns of balance, gravity shaping motion in intricate ways. Around them orbit planets, asteroids, and dust. Each star, no matter how faint, might have its own miniature solar system. In recent decades, we've confirmed thousands of exoplanets, worlds orbiting stars beyond our sun, and every discovery suggests there are far more waiting to be found. Statistically, there are likely more planets than stars in the galaxy. That means hundreds of billions of possible worlds, each unique, each spinning through its own story of light and gravity. When you realize that, the idea of counting begins to shift. The goal stops being about numbers and becomes about understanding relationships, how stars form, how they die, how they cluster into arms and move around the galactic center. The Milky Way is structured but fluid, like a living organism. Stars are born in dense clouds of gas and dust. As they ignite, their radiation pushes away the surrounding material, shaping the next generation of formation. Over time, they drift apart, pulled by the collective gravity of the galaxy. Some stay close together, forming star clusters. Others wander alone. The process is continuous, a balance between creation and dispersal that keeps the galaxy alive. In our region of the Milky Way, one of the spiral arms called Orion Cygnus, stars are spaced, on average, a few light years apart. That sounds close, but it's still trillions of kilometers between neighbors. If the Sun were the size of a marble, the next nearest star would be another marble placed several thousand kilometers away. Between them, nothing solid, only dust and darkness. Multiply that spacing by hundreds of billions, and you begin to glimpse the structure of the galaxy. Mostly empty, but filled with light spread across impossible distances. The stars don't form a crowd. They form a vast network, each one a node connected by invisible threads of gravity and motion. The Milky Way's spiral arms are regions where those stars are denser, where the balance of gravity and rotation compresses gas clouds just enough to trigger new birth. They're like waves in the ocean, patterns that move through material rather than fixed objects. Stars form within them, shine for a while, and drift out again, leaving room for the next generation. The spiral pattern we see from afar is the cumulative result of millions of years of movement. Counting stars isn't just counting points of light, it's counting motion, process, time. Each number represents something that has already changed, is changing, and will continue to change long after we stop observing. The way we map those stars depends on the light they emit. Some are visible, but many are hidden behind dust. To see them, astronomers use different parts of the spectrum: infrared, radio, X-ray, and more. Each wavelength reveals something different. Radio waves can pass through dust, showing stars in regions otherwise invisible. Infrared light reveals cooler objects like brown dwarfs, stars that never ignited fully. X-rays show the hottest, most energetic regions where matter is collapsing or exploding. By combining all these views, scientists build composite maps of the galaxy, layering colours of light we can't see into an image of the whole. It's a way of making the uncountable visible, if only in fragments. And yet, every time we think we've mapped it, we discover something new. The European Space Agency's Gaia mission, for instance, is currently cataloguing over 1 billion stars with unprecedented accuracy, measuring their positions, brightness, and motion. It's only a fraction of the total, but it's enough to create a living map of the Milky Way, a dynamic model where every star is tracked as it moves through space. From that data, astronomers can reconstruct the galaxy's history, tracing how it formed from smaller galaxies that merged billions of years ago. They can even predict its future, how it will change shape over the next few billion years as it interacts with its neighbours. Counting, in this context, becomes storytelling. The uncountable nature of stars isn't just about quantity, it's about time. Each star exists for millions or billions of years, going through stages of birth, maturity, and death. The galaxy isn't filled with identical lights, it's filled with processes at every phase of evolution. Some stars are newly formed, still wrapped in the gas clouds that created them. Others are middle-aged like the Sun, stable and steady. Still others are near the end of their lives, swelling into giants or collapsing into dense remnants. The light that reaches us carries all those ages at once, mixing them into a single view. When you look at the Milky Way, you're seeing history layered together, newborn light beside ancient echoes. Even the dark spaces between stars hold meaning. They're filled with molecules, hydrogen, carbon monoxide, traces of more complex compounds, drifting and waiting for gravity to gather them again. Those clouds are the next generation of stars in waiting. The galaxy recycles itself endlessly. The atoms in your body, the calcium in your bones, the iron in your blood, all of them were forged in stars that lived and died long before the sun was born. Counting stars, in a sense, is counting the ancestors of everything that exists. Every one of those billions of points of light has contributed something to the material of life. When we describe the Milky Way as having hundreds of billions of stars, it's easy to focus on the number and forget the individuality. But each of those stars has its own story, its own path, its own potential for worlds and perhaps even life. Somewhere out there, orbiting one of those countless suns, could be another planet with oceans, air, and people looking up and wondering the same things we do. If that's true, then the uncountable isn't just a matter of statistics. It's a measure of possibility, the vast range of what could exist waiting quietly in the dark. That possibility reshapes how we think about our own smallness. If there are hundreds of billions of stars and each might have planets, then there are hundreds of billions of chances for something like us to exist. Our place in the galaxy becomes less isolated and more like one instance in a grand pattern. The uncountable doesn't diminish our significance, it gives it context. We're part of a continuum so broad that the boundaries of meaning stretch beyond imagination. Every spark of light is both itself and a reflection of the whole. Trying to hold that scale in your mind for long can be dizzying. It's easy to lose sense of proportion, to feel the weight of distance and number pressing in. But there's also a kind of peace in it. Once you accept that the galaxy can't be counted in the ordinary sense, you can stop trying to reduce it to numbers and start letting it simply exist as it is. Vast, living, unmeasurable. The mind doesn't need to contain it to appreciate it. The act of wondering, of thinking about those countless stars, is itself a way of being part of the galaxy's unfolding story. So when we talk about counting the uncountable, what we're really doing is acknowledging the limit of comprehension and finding meaning beyond it. The galaxy doesn't ask to be tallied. It asks only to be seen, to be recognized as the environment that makes everything possible. Every atom, every light, every shadow belongs to it. The uncountable isn't a flaw in understanding. It's the natural state of something so large that even time and number bend under its scale. The galaxy isn't a static collection, but an ongoing process, one that continues whether or not we keep track. Our role, small as it is to notice it, to learn from it, and to carry that awareness back to our own little corner of the sky, where a single star continues to shine, steady and familiar among the uncountable others. When you look up at the Milky Way from Earth, what you see is only a fraction of its structure. To the naked eye, it appears as a pale, irregular band stretching across the sky. In photographs, it becomes a luminous arc filled with subtle colour and texture, a river of light winding through darkness. But what we see from within is only the cross-section of a much larger form, a spiral galaxy seen edge-on from the inside. From our position, about halfway between the centre and the edge, we look through the densest part of its disk. Every faint shimmer, every cluster, every hazy patch in that band is part of the same enormous structure turning slowly through space. The Milky Way isn't a solid object. It's a vast collection of stars, gas, dust and dark matter, held together by gravity and shaped by motion. Its spiral form is not a rigid shape, but a pattern, the result of billions of individual orbits, each following its own path yet together, creating the illusion of arms that curl gracefully outward. The galaxy is about 100,000 light-years across and roughly 1,000 light-years thick. It contains not only stars but also immense clouds of hydrogen, filaments of dust, and invisible halos of dark matter that extend far beyond what we can see. All of it moves in a slow, coordinated rhythm around the galactic centre. From the outside, it would look like a flat disk with a bright bulge in the middle, where stars are densely packed. Surrounding that disk is a faint halo, a diffuse sphere of old stars and clusters orbiting far from the core. The spiral arms extending outward from the centre are regions of higher density where new stars are born. They're not static structures. They move through the disk like waves of compression, gathering gas and dust as they pass. Inside those arms, stars ignite, live their lives and drift away, leaving the pattern to repeat. The Milky Way's gentle spiral is both movement and memory, a pattern that persists even though the material within it constantly changes. We can't see the whole structure directly because we're inside it. It's like trying to describe the shape of a forest while standing among the trees. Our view is limited to what we can measure and infer. Over time, astronomers have pieced together the picture using radio telescopes that can detect the faint emission from hydrogen gas. By mapping the motion of that gas, they've traced the spiral pattern of the arms. We now know that the Milky Way has a central bar, a stretched dense region of stars that cuts across the core, and from the ends of that bar, several major spiral arms emerge. Our solar system lies within one of the smaller arms, called the Orion Cygnus arm, nestled between two larger ones named Sagittarius and Perseus. When you imagine the galaxy from above, the spiral arms look like slow-turning currents in a vast whirlpool. Each arm contains countless clusters, nebulae, and star-forming regions. They're not rigid or sharply defined. They fade gradually into the spaces between, where the density of stars decreases but never reaches zero. The Milky Way's rotation is not uniform either. Stars closer to the centre orbit faster, while those near the edges move more slowly. This difference in speed is part of what maintains the spiral structure, a dynamic balance between motion and gravity. It's a kind of self-organising beauty, a shape that sustains itself through movement rather than design. At the heart of the galaxy lies the bulge, a dense region packed with old stars and dust. It's not spherical, but elongated, like the core of a seed. Buried within that bulge is something we can't see directly, a supermassive black hole known as Sagittarius A. It has a mass equivalent to about 4 million suns, yet it occupies a region no larger than our solar system. Its gravity is so strong that even light cannot escape, but we can detect its presence by watching how nearby stars move. They orbit the invisible centre at incredible speeds, their paths revealing the weight of something immense hidden in the dark. Sagittarius A is quiet most of the time, feeding slowly on surrounding material, but occasionally it flares, releasing bursts of energy that ripple through space. The discovery of that black hole changed how we understand galaxies. It seems that nearly all large galaxies have such a massive object at their core. The relationship between these central black holes and the galaxies that surround them is still a mystery. They might grow together, influencing each other's evolution over billions of years. The centre of the Milky Way, though distant and obscured by dust, is a place of intense activity. Stars packed so closely that they orbit within hours, clusters colliding, clouds of gas collapsing under pressure. It's a region that reminds us that even in the quiet, ordered spiral, there are places of chaos and energy. Farther from the core, where our solar system resides, the galaxy is calmer. Here, the stars are more widely spaced, and the spiral arms sweep through slowly, taking hundreds of millions of years to complete one turn. The Sun itself orbits the centre, at a distance of about 26,000 light-years, moving at roughly 200 kilometers per second. At that speed, it takes about 230 million years to make a full revolution. That means since the formation of the solar system, about 4.5 billion years ago, we've circled the galaxy roughly 20 times. Every orbit carries us through different regions, denser arms, quieter gaps, clouds of dust and open star fields. Our view of the sky changes slowly over geological time, though to us it feels fixed. The Milky Way's disk isn't flat like a record. It's slightly warped, its edges curling up and down in a gentle wave. This warp may have been caused by gravitational interactions with smaller galaxies orbiting nearby or by the uneven pull of dark matter surrounding it. The disk also vibrates subtly, like the surface of water disturbed by distant motion. These ripples move through the stars and gas over millions of years, shaping patterns we can only detect through careful measurement. Even at the galactic scale, motion never truly stops. The spiral arms, the stars, the gas clouds, All of it participates in a constant slow dance governed by gravity's patient hand. When you consider the sheer number of stars and the size of the structure that contains them, it's easy to think of the galaxy as static, something too large to change. But it evolves constantly. Stars form in the spiral arms, live their lives, and die, enriching the surrounding gas with heavier elements. Supernovae explode, scattering material that will one day form new stars and planets. The cycle repeats endlessly, each generation building on the remnants of the previous one. The Milky Way's spiral isn't just a shape, it's a process, a record of creation stretching across billions of years. If you could somehow rise above the disk and look down from a distance, the Milky Way would glow with a soft, diffuse light. Its arms would wind outward like trails of smoke, bright near the centre and fading toward the edges. From that vantage, you could see its neighbours too, small satellite galaxies like the large and small Magellanic Clouds orbiting nearby, drawn slowly inward by gravity. You might even see faint streams of stars, remnants of smaller galaxies that the Milky Way has absorbed in the past. Over its long history, it has grown by consuming others, their stars stretched into thin arcs that still circle the outskirts. The spiral we see today is partly the result of those interactions, a blend of order and memory written in starlight. Inside the disk where we are, perspective changes everything. The spiral arms we imagine as sweeping curves appear to us as dense regions of stars along the plane of the sky. When we look toward the galactic centre, in the direction of Sagittarius, the sky becomes crowded with light, the Milky Way at its brightest. When we look away, toward the outer edge, it thins into a faint shimmer. Between those extremes, dark lanes of dust cut through the glow like rivers of shadow. These are the same clouds that will one day form new stars. They block visible light, but shine faintly in infrared, revealing structure even in the places that look empty. It's in those dense lanes and glowing arms that we see the galaxy's balance most clearly. Destruction and creation existing side by side. A supernova explosion can sweep clean a region of gas, but the shockwave from that event can also compress nearby clouds, triggering the birth of new stars. The Milky Way sustains itself through that cycle. Nothing is truly lost, it's all transformed, moving from one form to another in the slow rhythm of galactic time. From the perspective of a single lifetime, it seems eternal. From the perspective of cosmic history, it's as transient as anything else, one of billions of galaxies, each with its own brief story in the lifespan of the universe. We sometimes imagine the spiral arms as static pathways, but they're more like waves travelling through a sea of stars. As those waves move, stars drift in and out of them. A star born in one arm may live long enough to move into another, or into the space between. The arms persist not because the same stars remain, but because new ones keep forming to replace them. It's a bit like traffic on a busy highway. The cars change constantly, but the pattern of motion remains. This is why the Milky Way's spiral form endures, even though every star within it moves independently. The rotation of the galaxy also reveals something invisible: dark matter. When scientists measured how fast stars orbit at different distances from the centre, they expected those farther out to move more slowly, just as planets in the solar system do. But they found that the speed stayed nearly constant, even at great distances. That meant there had to be more mass than we could see, something that doesn't emit or reflect light but still exerts gravity. This unseen material, called dark matter, forms a vast halo around the galaxy, outweighing all the visible stars and gas combined. We don't know what it's made of, but without it, the Milky Way's gentle spiral would not hold together. It would spin apart. The shape we see depends on something invisible, an unseen scaffold that keeps the galaxy intact. Even with all our instruments, the full picture remains incomplete. We can map the arms, measure the rotation, and model the structure, but much of the detail is still hidden by distance and dust. The galaxy's far side, opposite our position, is difficult to observe directly. We know it's there from symmetry and from faint radio signals, but it remains largely unseen. In that sense, we live in a place both known and mysterious, familiar enough to understand, but vast enough to remain beyond full comprehension. The Milky Way spiral is gentle not only in shape, but in its refusal to reveal everything at once. Thinking about this structure while lying under the night sky can make the mind feel weightless. Every point of light is part of the same rotating disk, and we are inside it, moving with it. The stars that appear fixed are actually tracing slow orbits around the galactic center. The sun's path carries us through arms and interarm regions, through clouds of gas and fields of empty space. The entire solar system is like a small passenger car on one of the outer lanes of an immense carousel, moving smoothly and silently in a motion too grand to feel. There's no vibration, no noise, no friction, just the steady drift of everything in unison. If you could watch the Milky Way's rotation sped up to a human pace, you'd see it turn gracefully, the arms winding and unwinding, stars lighting up and fading away. It would look alive, breathing in cycles of light. But at normal speed, those changes unfold over spans of time far longer than human history. The galaxy's spiral, for all its grandeur, is a picture of patience. Its motion stretched across eons, so slow that it becomes invisible, and yet constant enough to define the background of everything that happens here. When you think about how many generations of stars have lived and died within those arms, it becomes clear that our existence is woven into that long process. The atoms in your body, the carbon, nitrogen and oxygen, were formed in stars that once shone somewhere in the Milky Way's spiral. They lived, burned, exploded, and scattered their elements into space, where they eventually became part of the cloud that formed the sun and the planets. The spiral isn't just the structure of our galaxy, it's the history of everything that has ever existed here. It's the path through which matter cycles, the shape through which time itself seems to move. As we continue to observe and map it, the Milky Way spiral remains one of the most familiar yet unreachable forms in the universe. We can describe it, model it, even imagine standing outside it, but we will always see it from within, surrounded by its light. That vantage point defines our perspective, close enough to feel its pull, distant enough to never see it whole. And perhaps that's fitting. A complete view might leave no room for wonder. Seeing only a part allows imagination to fill the rest. If you look up tonight, and the sky is clear enough to see that faint river of light stretching across the darkness, you're looking through one of those spiral arms. You're seeing the shape of the galaxy from the inside, an edge-on glimpse of the structure that holds us all. The light you see has travelled for thousands of years, crossing the space between stars to reach your eyes. Each photon carries the signature of its origin, a reminder that we're part of a system so large and so smooth that even the smallest motion connects to something vast. The spiral continues to turn, indifferent to our sense of time, drawing us with it through the quiet geometry of the Milky Way. And as we drift with it, we remain surrounded by that same gentle structure, the luminous arms that guide our path through the galaxy, the subtle motion that never stops, and the unspoken rhythm that binds every star, planet, and molecule of dust into the same cosmic curve. When we try to describe where we are in the universe, it's natural to start small. We live on a planet that orbits a star. That star belongs to a galaxy we call the Milky Way. But the moment you try to expand that sentence beyond those simple facts, the scale begins to slip out of reach. Even describing our location within the galaxy requires language stretched beyond what our senses were designed for. The Milky Way is so vast, so layered, that to find our exact place within it feels a little like trying to describe a single grain of sand on an endless beach. Still, there is something quietly grounding about knowing that we can locate ourselves at all, that our small world has a definable address in the great galactic sea. Our solar system is situated in one of the Milky Way's minor spiral arms, a region known as the Orion Cygnus arm. It's not one of the major arms, like Sagittarius or Perseus, which sweep outward from the galactic centre in grand arcs. Instead, it's more like a smaller bridge of stars that runs between them, a calm stretch of the galaxy's disk with enough stability for planetary systems to thrive. You can imagine it as a quiet lane in a busy city, far enough from the dense downtown of the galactic core to avoid its chaos, but close enough to feel part of the structure. This small arm is our neighbourhood, the region of the Milky Way where the sun was born and where it has been travelling for billions of years. If you could see the galaxy from above, our position would be about 2/3 of the way out from the centre, roughly 26,000 light-years away. That might sound close in the context of the galaxy's size, but light itself takes 26,000 years to cross that distance. In more familiar terms, it's around 250 quadrillion kilometres. These numbers are so large they stop feeling like numbers at all. They become markers of proportion, a reminder that the sun, the planets, and everything that has ever happened on Earth exist within a small pocket of space, halfway along one of the galaxy's spiral arms. We orbit the galactic centre at a speed of about 220 kilometers per second. Even at that pace, it takes more than 200 million years to make a single revolution. Since the solar system formed, we've completed only about 20 full orbits. Every time Earth goes around the sun itself has moved slightly along its own path through the galaxy. We're never in the same place twice. The stars that appear fixed in the sky are moving too, each tracing its own slow curve around the galactic core. The patterns we call constellations are temporary alignments, meaningful only on the scale of a few thousand years. On the scale of the galaxy, they drift apart like clouds. The space around us is not empty. It's filled with stars, dust, and gas, though spread so thin that even the nearest stars are separated by light years of distance. The nearest major star to the Sun, Alpha Centauri, lies about 4.37 light-years away. Between us and it lies a vast region of space containing only a handful of atoms per cubic centimetre. And yet, that same region is part of the continuous fabric of the galaxy. The light that leaves our sun travels through it, blending with the light from other stars, filling the space between them with a faint collective glow. The galaxy's disk is like an ocean of light and matter, dense near the centre and sparse near the edges, but continuous throughout. When we say that we live in the Milky Way, it's more accurate than it sounds. The Sun and its planets orbit within a thin disk about 1,000 light-years thick. Most of the galaxy's stars, gas and dust are contained within that disk. Above and below it, the density drops quickly, giving way to the galactic halo, a vast, diffuse region populated by older stars and globular clusters. The disk itself is slightly warped, curving upward on one side and downward on the other. From our vantage point, we lie close to the midplane, not exactly centred, but well within the main body of the galaxy. The environment here is relatively calm compared to other regions. The density of stars is low enough that the gravitational influence of nearby suns doesn't disturb the stability of planetary systems. That calmness is one of the reasons life could develop on Earth. Closer to the centre of the galaxy, stars are packed so tightly that their radiation and gravitational interactions create a far more volatile environment. Farther out, beyond the spiral arms, the density drops so much that there may not be enough heavy elements for planets to form. Our position between the extremes is something astronomers sometimes call the galactic habitable zone. It's not an official boundary, but it describes a region where conditions are just right, not too crowded, not too sparse. From within the disk, we can't see the galaxy's full shape directly, but we can infer it from the way stars move. The Sun and nearby stars orbit the centre in nearly circular paths, guided by the combined gravity of everything in the galaxy: stars, gas, dust, and the unseen dark matter that forms its invisible halo. That halo extends far beyond the visible edge, providing most of the mass that keeps the spiral structure intact. Without it, the outer regions would spin apart. Our orbit, though fast, is steady, part of a balanced motion that has persisted for billions of years. The galaxy's gravitational field is strong enough to hold us, but gentle enough to let us move freely within it. The region around the Sun is sometimes called the local bubble, a cavity in the interstellar medium created long ago by supernova explosions. The gas here is thinner and hotter than in surrounding areas, suggesting that a series of ancient stellar deaths cleared out the space around us. The Sun happens to reside near the edge of this bubble, in a region where the density of interstellar gas is beginning to rise again. It's likely that as we continue our orbit, the solar system will eventually drift into denser regions of the galaxy, encountering new clouds of gas and dust. On a human timescale, that journey is imperceptible, but over millions of years it will subtly change our environment. Our address within the Milky Way, if written out, would sound like something halfway between a poem and a scientific coordinate. The third planet orbiting a G-type main sequence star, located in the Orion Cygnus arm of the Milky Way galaxy, approximately 26,000 light-years from the galactic center, moving at 220 kilometers per second through the galactic disk. It's factual, but it's also a description of belonging. It tells us not only where we are, but how we move. A reminder that our position is not static, that we are part of an ongoing flow through this galaxy's structure. It's easy to think of the Milky Way as an external object, a vast thing that we're observing from the outside. But we are inside it completely. Every direction you look, you're looking into the galaxy. Even the empty parts of the sky are filled with its faint light, its distant stars. The galactic center lies in the direction of the constellation Sagittarius, and if you could see through the dust that blocks visible light, you would find an overwhelming brightness there. Radio and infrared observations reveal the crowded heart of the galaxy. Dense clusters of stars, clouds of gas glowing with energy, and the gravitational dominance of the central black hole. In the opposite direction, toward the constellation Auriga, you look outward toward the galaxy's edge, where stars grow fewer and darkness takes over. Knowing our place within that layout helps us understand the view we see each night. When the Milky Way arches across the sky, we're looking through the plane of the disk, our line of sight cutting through layers of stars. The densest parts correspond to where we're looking toward the center, while the thinner regions are where we look outward. That's why the band appears brighter in one direction and dimmer in another. We're seeing the galaxy's structure not as a whole but as a cross-section, an interior view of our own home. If you could travel far above the disk, you'd see the Milky Way as a flattened spiral, its arms winding outward from the glowing center. From that perspective, our solar system would be invisible to the eye, even with the best telescopes. The sun's light would blend into the general glow, indistinguishable from billions of others. Yet within that vast field of light, everything familiar, every tree, ocean and thought, would still be there, carried along on one small dot orbiting one ordinary star. Our sense of scale might vanish from such a distance, but our sense of continuity would remain. No matter how far you move away, the galaxy's light would still include ours, faint but present. Around us, within a few dozen light-years, lies what astronomers call the solar neighborhood. It includes nearby stars like Alpha Centauri, Sirius, Epsilon Eridani, and Procyon. Many of these have their own planetary systems. From their vantage point, our sun would appear as just another bright star, a modest yellow point among many. The idea that each of those stars might have its own worlds, its own forms of light and shadow, gives our neighborhood a sense of quiet depth. The galactic sea is not empty between its major currents. It's filled with islands of light, each with its own system, its own rhythm, and its own history. The scale of that sea becomes clearer when we look at the distribution of stars. Near the galactic center, They are densely packed, thousands per cubic light year. Out here, near the edge of one arm, the average distance between stars is several light years. That spacing creates the illusion of isolation, but it's also what makes our region stable. Fewer close encounters mean less disruption. Over billions of years, that stability has allowed planetary systems to remain intact long enough for life to develop. We exist not because we are at the centre of anything, but because we are far enough from chaos to endure. Above and below the galactic plane, the halo of the Milky Way extends outward for tens of thousands of light years. It's filled with ancient stars and clusters that formed early in the galaxy's history. These globular clusters orbit the centre in long looping paths that carry them far above the disk before swinging back through it. They're relics of a time when the Milky Way was still forming, merging with smaller galaxies and gathering matter from its surroundings. Some of those early collisions left streams of stars that still trace arcs through space, faint reminders of the galaxy's ongoing evolution. The Sun's position in this larger structure is stable for now, but nothing in space stays fixed forever. Over the next 100 million years, the solar system will continue its slow orbit, passing through different parts of the galactic disk. Occasionally, it may encounter regions of higher density, spiral arms rich with gas and new stars, before moving back into quieter spaces. These passages could subtly influence conditions on Earth. Some scientists speculate that as we move through regions with more interstellar dust, the influx of cosmic particles might affect climate or evolution. The galaxy is vast, but its patterns still reach down to the scale of individual worlds. Thinking about our position this way, not as a static point but as part of a moving system, changes how we see everything else. We often imagine ourselves as stationary observers, watching the stars move around us, but in reality we're the ones moving through their field. The galaxy doesn't turn around us. We travel within it, carried by its rotation, bound to its structure. Every sunrise, every orbit, every moment on Earth unfolds within that continuous motion. Even if we never feel it, we're in constant flight, gliding through the galactic sea along with billions of others. The term galactic sea is fitting because the Milky Way behaves like an ocean. Its stars are like waves, rising and falling in patterns that repeat but never stay the same. The currents are gravitational, flowing between clusters and arms, guided by the mass of dark matter beneath. We're a small part of that movement, floating on a current we didn't create and can't control, but that carries us all the same. The sense of being at home within something so large comes not from knowing every detail but from realizing we belong to the motion itself. If you imagine standing on a distant planet, orbiting a star in another arm of the Milky Way, our position would seem almost identical to theirs. A small point in the disk midway between the centre and the edge, moving through the same slow rotation. From that perspective, the idea of an address becomes relative. There are no fixed coordinates in a galaxy that's always in motion, only relationships between moving parts. What we call location is really participation, the specific place where our motion intersects with everything else. The beauty of knowing our galactic address is that it gives scale to our perspective without shrinking it. We are small, yes, but not misplaced. We occupy a stable orbit in a quiet arm of a spiral galaxy that has existed for more than 10 billion years. Everything we know fits into that context, a single system among billions, each one contributing its own light to the whole. It's not a position of insignificance, but of integration. We're part of the pattern, shaped by it, sustained by it, and destined to move with it through time. And as we continue along that path, the view will shift slowly, invisibly. The constellations will change. New stars will appear as old ones fade. The galaxy's arms will rotate, and we'll pass through them again and again, carried by the same invisible current. Every orbit adds another layer to our story, another turn in the quiet spiral of motion that defines the Milky Way. Somewhere within that slow rhythm we remain anchored, a small solar system in the Orion Cygnus arm, circling the galactic centre, surrounded by stars and dust and light. That's our address, our location in the great sea of the galaxy, and while we'll never see it from the outside, we can still sense it every time we look up and realise that every point of light above us is part of the same vast home, turning silently through space. When you try to imagine the distances that exist beyond Earth, it quickly becomes clear that ordinary intuition doesn't work. Our minds are built for the scale of daily life. Meters, kilometres, maybe thousands of kilometres if we think about continents or oceans. Those are distances we can picture, because we can cross them, measure them, and see their edges. But when we step beyond the boundaries of our planet, those familiar anchors disappear. The space between worlds, between stars, between galaxies, expands so far beyond our senses that the words we use to describe it lose meaning. Even numbers, precise as they are, start to feel abstract, like symbols for something the human mind was never meant to hold. To begin understanding that scale, it helps to start small, or at least small by cosmic standards. The Earth is about 12,700 kilometres across. The Moon is nearly 400,000 kilometres away. It takes light a little more than a second to cross that gap. That already feels large, and yet the distance between Earth and the Sun is 300 times greater. We call that span 1 astronomical unit, about 150 million kilometres, and even that is still tiny compared to the rest of the solar system. Neptune, the outermost of the major planets, is 30 astronomical units from the Sun. It takes light over 4 hours to reach it, from the Sun to the edge of the solar system, where the influence of its wind fades into interstellar space, is more than 100 astronomical units. Beyond that lies the Oort cloud, a shell of icy bodies that stretches perhaps 100,000 astronomical units in every direction. At that distance, the Sun's light takes more than a year and a half to reach the outer edge. The boundary between the solar system and interstellar space isn't a line, it's a gradient of fading influence. When you consider those scales, it becomes obvious why the distances between stars are so hard to imagine. The nearest star system, Alpha Centauri, lies more than 4 light-years away, 40 trillion kilometres. Compared to that, even the vastness of the solar system looks compact. A light-year is the distance light travels in 1 year, about 946 trillion kilometres. It's a unit that replaces impossibly large numbers with a smaller word, but it doesn't make the reality any easier to grasp. When astronomers say a star is 10 light-years away, they mean its light has been travelling toward us for 10 years. 100 light-years means 100 years of travel at the fastest possible speed in the universe, and that's still nothing compared to the size of the galaxy. The Milky Way is about 100,000 light-years across. Light leaving one edge will take 100,000 years to reach the other. Every time you see the faint band of the Milky Way across the sky, you're looking through that immense distance, a field of light so large that even at the speed of light, crossing it would take longer than all of recorded human history. The problem with thinking about such distances is that we naturally try to visualize them. We imagine travelling from one point to another as if space were a landscape we could cross, but the scale defeats that approach. No vehicle, no technology we've built or imagined can come close to the speed needed to make such journeys reasonable. The Voyager spacecraft, the most distant human-made objects, are still within the outer edges of the solar system after almost 50 years of travel. They're moving fast by any normal standard, about 60,000 kilometers per hour. But at that speed they would need more than 70,000 years to reach the nearest star. It's not that the galaxy is unwelcoming, it's simply enormous in a way that makes motion itself seem slow. If you tried to build a model of the solar system that fit into something you could walk across, you'd quickly run into problems of scale. Suppose you made the Earth the size of a marble, about 1 centimetre across. On that scale, the Moon would be a smaller bead a few centimetres away. The Sun would be a ball more than a metre across, about 100 metres away from the Earth. The outer planets would be scattered across a space several kilometres wide. And the nearest star? It would be another meter-wide sphere placed more than 2,000 kilometers away. Between them, nothing but emptiness. This is what makes space so difficult to comprehend. Our everyday experience teaches us that distance is defined by things, roads, oceans, mountains, places to stop. But most of the universe is not made of things. It's made of space itself. The distances are not filled with matter, not populated by objects, but open. The fraction of the galaxy occupied by stars, planets, or dust is almost zero compared to the vastness of the gaps between them. The Milky Way, though dense with hundreds of billions of stars, is mostly vacuum. If the Sun were the size of a coin, the nearest other star on that scale would be another coin placed tens of thousands of kilometers away. The space between them would be empty enough to fit millions of other coins without a single collision. Even within galaxies, the distances between stars are so large that their light rarely meets. Photons travel freely through the interstellar medium, occasionally scattered by dust, but mostly unimpeded. That's why we can see stars at all. If space were crowded, their light wouldn't reach us. The emptiness is what makes the view possible. The Milky Way's soft glow in the night sky is a collective illusion. Countless stars seen together from a great distance. They seem close because their light overlaps, but they are separated by light years of emptiness. We've developed ways to measure these distances, though even our tools strain against the scale. For nearby stars, astronomers use parallax, the apparent shift in a star's position as Earth moves around the Sun. By measuring that tiny angle, they can calculate the star's distance. The effect is so small that even for the nearest stars the shift is barely detectable. For example, Alpha Centauri's parallax is less than 1 arcsecond, about the same as seeing a coin move 1 centimeter when viewed from several kilometers away. For more distant stars, parallax becomes too small to measure directly, and we rely on brightness and spectral characteristics instead. We compare the observed light to what we expect from similar stars and infer distance from how faint it appears. Each method adds a layer of approximation, and yet through patient measurement, we've mapped the galaxy with remarkable accuracy. When we extend our view beyond the Milky Way, the numbers grow even harder to hold. The nearest large galaxy, Andromeda, is about 2.5 million light-years away. That means the light we see from it tonight left before the earliest humans walked the Earth. The galaxies we see at the edge of the observable universe are so far away that their light has been travelling for more than 13 billion years. We're not seeing them as they are, but as they were when the universe was young. The space between us and them has expanded since that light began its journey, stretching the light's wavelength and dimming its colour, an effect we call redshift. Every distant galaxy is both a picture of the past and a measurement of distance written in colour. Distances like these change how we think about time. When you look at the stars, you're looking back into history. Even the light from the Sun is 8 minutes old. From Sirius, it's 8 years. From the Pleiades, about 400. When you look at Andromeda through a telescope, you're seeing a galaxy as it was when the first fires burned in human settlements. Time and space blend together so completely that it becomes difficult to separate them. Every point of light in the night sky is also a point in the past. The farther you look, the older the image. This connection between distance and time isn't just poetic, it's physical. The speed of light is the ultimate limit. Nothing can move faster. That means information itself is bound by distance. We can't see the present state of faraway objects. We can only see their past. Even if a distant star exploded right now, we wouldn't know until its light reached us, possibly centuries later. The universe is a network of delayed signals, each place seeing every other as it was long ago. The closer you are, the more current your view. The farther you go, the older the picture becomes. In that sense, the cosmos is both vast and full of memories, carrying light from moments that ended long before we were here to witness them. When we measure these scales, the numbers themselves can lose meaning. It's easy to say a light year or a parsec, but each one represents a physical span that's incomprehensible without context. To give perspective, the fastest spacecraft ever launched by humanity, travelling at tens of kilometres per second, would take tens of thousands of years just to reach the nearest star. The diameter of our galaxy, measured in light years, would take hundreds of millions of years to cross at that speed. The nearest large cluster of galaxies, the Virgo cluster, is more than 50 million light years away. These are distances so great that even at the speed of light, communication between such regions would take longer than the lifespan of entire species. Because of this, the universe we see is always only a small local version of the whole. The observable universe, the part from which light has had time to reach us since the Big Bang, is about 93 billion light years across. Beyond that, space continues, but we can never see it. Light from those regions hasn't had enough time to arrive. The horizon of visibility isn't the edge of reality, it's the edge of information. We're inside a bubble defined not by walls, but by time itself. The distances beyond remain theoretical, though we know they exist. Even within that bubble, distances defy ordinary comparison. Between the planets, we measure in millions of kilometres, between stars in light years, between galaxies in millions of light years, between clusters of galaxies in hundreds of millions. Each step up in scale adds zero so quickly that perspective collapses. The human mind wasn't built for such quantities. We evolved to navigate valleys, not voids. But through mathematics and imagination, we can extend our sense of place, building conceptual bridges across scales that we'll never physically cross. There's something strangely peaceful about that realization. The sheer size of the universe doesn't make us small in the way we sometimes fear. It makes us part of something continuous. The same laws that govern falling apples and orbiting planets also govern the motion of galaxies. Gravity doesn't care about scale. Light behaves the same way whether it travels across a room or across a galaxy. The distances may defy intuition, but the principles remain steady. That continuity links us to everything else, making the impossible size of the universe feel less alien and more like an extension of what we already know, stretched beyond sight. Sometimes astronomers use analogies to help make these distances feel less abstract. They might describe the galaxy as a city, where each star is a house and the spaces between them are miles of empty land. Or they might compare the observable universe to the surface of a balloon expanding, where galaxies are like dots on its skin, carried farther apart as the balloon inflates. These comparisons don't capture the full reality, but they give a sense of motion and scale that our everyday experience lacks. They remind us that distance isn't just static space. It's dynamic, shaped by time, motion, and gravity. Even in the emptiest reaches of the universe, there is structure. Galaxies cluster together, forming filaments that stretch across hundreds of millions of light years. Between them lie vast voids, regions where almost no galaxies exist at all. The pattern resembles a web, a cosmic lattice of light and darkness. Our own Milky Way is part of one of those filaments, connected to neighbouring galaxies through invisible threads of gravity. The spaces between clusters are so large that entire galaxies could drift through them without ever meeting another for the lifetime of the universe. These are distances that can't be walked, flown, or even meaningfully imagined, only calculated and acknowledged. It's tempting to think that such vast separations make the universe disconnected, but in reality those gaps are part of its structure. The expansion of space itself creates them. Everything we see, every star, every galaxy, moves away from every other on large scales. The distances grow not because things are moving through space, but because space itself is stretching. The farther apart two galaxies are, the faster they appear to move away from each other. It's not motion in the ordinary sense, it's the fabric of the universe expanding everywhere at once. That's why there's no true centre. Every point can be considered the middle, because the expansion happens uniformly in all directions. When you realise this, the word distance takes on a new meaning. It's not just a measure between two objects, it's a measure of time, expansion, and change. Every span between stars or galaxies carries a history of movement. The light that crosses those spans brings information from one moment to another, turning the universe into a kind of record. The vastness we can't imagine isn't empty or static. It's full of relationships, written in light and gravity, stretched across time. Even though we can't intuitively feel these distances, we can still measure them, describe them, and use them to understand our place. We can point to a galaxy millions of light years away and know that its light has travelled for eons to reach us. We can trace the curvature of space itself and see how matter bends light over cosmic scales. Through observation, the unimaginable becomes measurable. We may never truly comprehend what 100,000 light years feels like, but we can still know what it means. That's what science offers, not comfort through familiarity, but clarity through understanding. So when you look at the night sky and see the faint scattered stars, remember that the light reaching you has crossed distances that defy every human sense of scale. It has travelled through regions so vast and empty that even words like space seem too small. Each glimmer is a signal from a different time, a reminder that we live within a structure of distances so immense that they become their own kind of silence. And yet, within that silence, there's order, motion, and connection. The quiet geometry of the universe continuing endlessly beyond the limits of intuition. Even when everything appears still, nothing in the universe is truly at rest. The world beneath you turns quietly, carrying you through day and night. The planet orbits the sun at 30 kilometers every second. The sun itself moves through the galaxy at hundreds of kilometers per second, and the galaxy in turn drifts through the larger structure of the universe, carried along by gravitational currents that never stop. The stillness we feel is only relative. Motion is constant, continuous, and everywhere. It's so vast and smooth that we never notice it. The air doesn't rush past us, the ground doesn't tremble beneath our feet. But we are always in motion, part of a silent drift that extends from the smallest particles to the largest structures in existence. If you could somehow stop everything else and look at the solar system from far away, you'd see it moving like a small bead following a track. The sun leads, and the planets orbit it, all together travelling around the centre of the Milky Way. The path isn't a perfect circle, but a slightly elliptical arc, tilted and curved within the galactic disk. Every object within that system, Earth, the Moon, the asteroids, moves together in a synchronized glide. Nothing stands still, yet everything maintains its position relative to the whole. The balance is so stable that the same orbits have persisted for billions of years. This motion around the galactic centre defines much of our existence, even though it's completely invisible to us. The Sun travels at roughly 220 kilometers per second, and yet we feel nothing because there's no resistance. Space offers no drag, no friction, no air to push against. In this vacuum, motion is silent and perfect. The Earth, the planets, and the Sun all fall together under the pull of the galaxy's gravity, circling an unseen centre where billions of other stars are also in orbit. The result is a kind of cosmic calm, constant movement without turbulence. If you could look down on the Milky Way from above, you'd see stars tracing elegant spirals, each one moving at its own speed but maintaining a collective rhythm. The galaxy rotates once every 230 million years, and though that may seem slow, the distances involved are so great that the motion adds up to immense speeds. Every star participates in that rotation, each orbiting the same gravitational centre, but never colliding. The space between them is wide enough that even as they move in vast numbers, direct contact almost never happens. It's a quiet traffic pattern on a scale beyond comprehension. The Sun's path isn't perfectly smooth. As it orbits the galactic centre, it also oscillates up and down through the disk, rising and falling like a boat on a slow tide. Each cycle takes tens of millions of years. When it passes through the densest part of the disk, it encounters more dust, gas, and gravitational influence. When it moves above or below, it enters quieter regions. Some scientists have speculated that these oscillations might subtly influence conditions on Earth, perhaps by increasing exposure to cosmic radiation or altering the number of comets that enter the inner solar system. Whether or not those effects are real, the image of our solar system bobbing gently through the galactic plane is an accurate one. We are passengers in a slow wave, lifted and lowered by the gravity of billions of stars. Beyond the boundaries of the Milky Way, the galaxy itself is moving. It's part of a small cluster of galaxies known as the Local Group, which includes Andromeda, the Magellanic Clouds, and a few dozen smaller companions. Within this group, each galaxy moves relative to the others, their mutual gravity binding them together. The Milky Way and Andromeda, the two largest members, are on a slow collision course. They're currently about 2.5 million light-years apart, approaching each other at around 110 kilometers per second. That might sound fast, but the scale is so large that they won't meet for another 4 billion years. When they do, their stars will mostly pass harmlessly by each other, their gravity reshaping both galaxies into a new form. The orbits of planets like ours may shift slightly, but space is so empty that direct collisions between stars are unlikely. The merger will be grand but silent, an event of light and gravity playing out over billions of years. Even now, the Milky Way moves through a larger structure called the local sheet, which includes several nearby groups of galaxies. The entire sheet drifts toward a region known as the Virgo cluster, a massive concentration of galaxies that exerts a gravitational pull across tens of millions of light years. Our motion toward that cluster is part of an even larger flow. The galaxies of our local region are all being drawn toward an immense gravitational center called the Great Attractor, located hundreds of millions of light years away. This movement isn't chaotic. It's part of the large-scale structure of the universe. Galaxies gather in clusters, clusters form superclusters, and those superclusters flow together along filaments of matter that stretch across the cosmos. Every level of structure participates in motion shaped by gravity, an invisible network connecting everything. When you think about that, it becomes clear that the concept of being stationary is only ever local. You can stand still relative to the ground, but the ground is turning with the Earth. The Earth is orbiting the Sun is orbiting the galactic center, the galaxy is moving toward other galaxies. Even those larger flows exist within a universe that's expanding in all directions. There is no fixed point in space where you could stop and say, this is absolute rest. Everything is in motion relative to something else. Stillness is an illusion created by shared movement. This motion, though enormous in scale, is balanced by time. It's so slow that on a human level it's invisible. The constellations we see in the night sky look the same today as they did thousands of years ago, but they're gradually changing. Over millions of years, those familiar patterns will distort as stars drift along their individual paths. Eventually, entirely new constellations will form. The night sky we know is temporary, a passing arrangement within the long flow of galactic motion. But it changes so slowly that for us it feels eternal. We live inside a moment that lasts for ages. The idea that everything is drifting can feel unsettling at first. We like to think of home as fixed, as something solid in a moving world. But in cosmic terms, everything we call stable, the continents, the oceans, even the sun, is in motion. The comfort comes from realizing that motion is normal. It's the background state of the universe. Even atoms vibrate constantly. The spaces between galaxies expand. The planets circle endlessly, and gravity maintains their order. The quiet drift of cosmic motion isn't chaos. It's equilibrium in motion. It's what allows the universe to exist without collapsing or freezing. If you could see motion on these scales sped up, it would look like a slow dance of light. Galaxies turning, merging, drifting apart. clusters forming webs of gravity that stretch and shift like breathing fabric. The Milky Way's spiral arms would unwind and wind again, stars circling in smooth patterns while new ones ignite in the gaps. To watch it in real time would take more than a lifetime. It would take all of human history multiplied many times. The universe moves on a timeline that dwarfs every story we know, and yet that same motion happens right now, continuously, all around us. The calmness of this motion hides the energy it represents. Every object with mass influences every other, no matter how far away. Gravity acts across all distances, weak but persistent. It shapes the paths of planets, stars and galaxies, curving space itself. The quiet drift we experience is the visible expression of that curvature, a universe shaped by the pull of everything on everything else. It's easy to forget that when we look at the sky, we're seeing not just points of light, but trajectories. Every star following a curve through space-time. Those curves define the geometry of the cosmos. The expansion of the universe adds another layer to this motion. While galaxies move within their clusters under gravity, space itself expands between clusters. This isn't like objects moving through space, it's the stretching of space itself. The farther apart two galaxies are, the faster they appear to move away from each other. That expansion carries everything with it, like dots on an inflating balloon. The galaxies themselves aren't flying outward through pre-existing space. They are part of the fabric that stretches. This means that even the quiet drift of our galaxy is embedded within a larger flow, a movement that has been ongoing since the beginning of time. When astronomers measure this expansion, they describe it in terms of redshift, the stretching of light as space expands. The more distant a galaxy is, the more its light shifts toward longer wavelengths. That shift tells us not only how fast it's moving away, but also how long its light has been travelling. By mapping these shifts, scientists can trace the structure of the universe and see how matter flows through it. The pattern that emerges is not random. It looks like a web, vast filaments of galaxies and clusters connected across unimaginable distances, separated by enormous voids where very little exists. The Milky Way lies along one of those filaments, moving with its neighbours through the cosmic web. Our drift isn't isolated, it's part of the flow of everything. Even within that grand structure, smaller motions persist. Stars within galaxies orbit their centres, planets orbit stars, moons orbit planets. The hierarchy of motion extends downward indefinitely, each scale nested within another. The quietness of it doesn't mean it's simple, it means it's balanced. The universe achieves stability through motion. Every orbit, every rotation, every expansion serves to distribute energy, to maintain equilibrium. If anything were truly still, gravity would pull it inward until motion began again. Stillness, in physics, is temporary. Motion is permanent. Our position within this network of motion is not random. The solar system moves in a particular direction through the galaxy, toward a point in the constellation Hercules. The entire Milky Way moves toward the Great Attractor, a region of space so massive that its gravity influences hundreds of thousands of galaxies. And beyond even that, there's another pull, toward a still larger structure called the Shapley supercluster. The farther we look, the more layers of motion we find, each one part of a larger flow. The universe has no single centre, only centres within centres, each defined by the gravity of its contents. It's humbling to realise that every moment of our lives unfolds within this quiet drift. The motion is constant, but it's also predictable. The same forces that carry galaxies across space hold us to the Earth, keep the moon in orbit and guide the planets around the sun. The same laws describe the path of a falling leaf and the orbit of a galaxy. Scale changes, but the rules do not. That consistency is what allows us to make sense of the universe at all. We can't feel the motion, but we can understand it, measure it, and even predict it millions of years into the future. Sometimes, when scientists simulate the universe's evolution on supercomputers, They see this motion play out in slow elegance. Clouds of matter collapse into galaxies. Galaxies form clusters. Clusters flow along filaments. Over billions of years, the patterns evolve, but the overall shape, the cosmic web, remains. It's a structure that looks alive, though it isn't alive in the biological sense. It's the physical outcome of gravity acting over time. What we call the quiet drift of cosmic motion is that same process, continuing everywhere, shaping everything we see. Even within the small scale of the solar system, the idea of rest doesn't really exist. The Earth rotates once every 24 hours, orbits the Sun once every year, and follows the Sun through the galaxy. The Moon moves around the Earth, and both move together around the Sun. Every atom in your body moves with that same rhythm, participating in each layer of motion simultaneously. When you sit still, reading or thinking, you're in fact spinning, orbiting, and drifting through space at tremendous speed. The silence of it doesn't mean it's not happening. It only means that motion at this scale feels like stillness, because everything near you shares it. It's worth noticing that this constant motion doesn't lead to instability. Quite the opposite. It creates the conditions for balance. The Earth's orbit keeps its temperature within a range that allows life. The galaxy's rotation keeps its structure intact. The expansion of the universe prevents everything from collapsing back into a single point. Motion distributes energy evenly enough for complexity to arise. Without it, there would be only compression and stillness, and neither could sustain the universe as we know it. From a certain perspective, this quiet drift connects everything. The atoms that make up your body were once part of stars that orbited other parts of the galaxy. Those stars drifted and died, scattering their elements into space, where they mixed with gas and dust that eventually formed the Sun and Earth. The particles that make you are still in motion, orbiting, vibrating, part of the ongoing circulation of matter and energy. Cosmic motion isn't something separate from us. It's the background condition that defines our existence. It can be difficult to appreciate that while we move through space, space itself also moves through time. The universe is not static but dynamic, expanding, cooling, and changing. Galaxies shift positions, clusters stretch apart. The large-scale pattern of motion continues, even as local systems like ours maintain their internal balance. Everything flows, but within that flow are stable eddies. Stars, planets, life. The stillness we experience on Earth is one of those eddies, a calm region within a sea of constant movement. If you could somehow watch the entire history of the universe unfold in a single glance, you'd see motion at every scale. Matter clumping together under gravity, collapsing into stars, forming galaxies, merging into clusters. You'd see waves of energy from ancient explosions spreading outward, rippling across the cosmic web. The quiet drift that we experience now would look, in that view, like a vast coordinated dance. Billions of points moving together according to simple, unbreakable rules. From within, it feels still. From outside, it's endless motion. And through all of it, there's no sound, no visible sign of speed, no sense of acceleration. Just the slow, steady flow of everything toward everything else, shaped by gravity, stretched by expansion, guided by the same principles that hold atoms together. We live within that motion, surrounded by it, dependent on it, though we rarely think about it. It's the quiet background of existence, the constant drift of the cosmos carrying us forward through space and time. When you imagine the Milky Way, it's easy to think of it as an isolated system, a single spiral of stars floating in a sea of darkness, complete within itself. But our galaxy doesn't exist alone. It's part of a small community of galaxies bound together by gravity, known as the local group. This group is like a neighbourhood within the larger universe, a collection of more than 50 galaxies, large and small, each moving in quiet orbits around a shared centre of mass. Some are grand spirals like our own, others are faint, irregular systems made of only a few million stars. Together they drift through space, bound not by contact but by the mutual pull of gravity that links them across millions of light years. The Milky Way is one of the two dominant members of this group. The other is the Andromeda Galaxy, a slightly larger spiral about 2.5 million light-years away. The two are remarkably similar in structure, each with sweeping spiral arms, a dense central bulge, and hundreds of billions of stars. Andromeda is the nearest galaxy of comparable size to ours, bright enough that under dark skies it can be seen as a faint smudge without a telescope. That blur of light in the constellation Andromeda is an entire galaxy, containing perhaps 1 trillion stars, along with planets, gas clouds, and star clusters. When you look at it, you're seeing light that left its stars before humans existed, travelling all that time across intergalactic space to reach us. Between the Milky Way and Andromeda lie smaller galaxies, companions and satellites that orbit around the two giants like distant moons. The Milky Way itself has more than 50 known satellite galaxies, though most are small and faint. The most visible of these are the large and small Magellanic Clouds, which can be seen from the southern hemisphere as two diffuse patches of light. They are irregular galaxies, much smaller than ours, containing only a few billion stars. Both orbit the Milky Way in elongated paths, interacting with each other and with our galaxy's gravitational field. Streams of gas connect them to the Milky Way, evidence of their ongoing exchange of material. Over time, these satellites are gradually pulled apart, their stars stretched into thin trails that wrap around the galaxy. Other satellites, like the Sagittarius Dwarf and the Canis Major Dwarf, are even closer, so close that they're already being absorbed. The Milky Way's gravity has drawn them in, tearing them apart and mixing their stars into its outer halo. Some of the stars we see in the sky today were once part of these smaller systems. This process of merging and accretion has been happening for billions of years. The Milky Way has grown not by forming all its stars in place but by consuming others. Its smooth spiral arms and halo are built from the remnants of galaxies long vanished, their structures erased but their stars still orbiting within ours. The same process continues on larger scales. Andromeda too has its own satellites, smaller galaxies that orbit and interact with it, just as ours do. The gravitational pull between the Milky Way and Andromeda is slowly drawing the two together. Their mutual attraction overcomes the expansion of space at this local scale, meaning that rather than drifting apart like most galaxies in the universe, they are moving toward each other. In about 4 billion years, they will collide and merge, forming a new, larger galaxy that astronomers sometimes call Milkomeda. The event will not be a violent crash in the ordinary sense. The space between stars is so vast that direct collisions are rare. Instead, the two systems will pass through each other, their gravitational fields distorting and reshaping both, sending stars into new orbits and triggering waves of star formation as clouds of gas compress. The process will take hundreds of millions of years, a slow blending rather than an explosion. When the merger is complete, the new galaxy will likely be an elliptical, smoother and rounder than the spiral forms we see today. Our Sun, if it still exists then, will be a quiet, fading star in its late stages, drifting within that new structure. The night sky from Earth, or whatever remains of it, would look dramatically different. Andromeda would grow larger each million years, eventually dominating the view, its spiral arms stretching across the horizon. Then, as the galaxies merge, the sky would fill with new stars, glowing with the light of countless suns scattered across the heavens. Even though no human will see it, the future of our galaxy is one of transformation, part of a process that has been occurring across the universe since its beginning. The local group itself is a modest structure in cosmic terms. It spans about 10 million light-years across, a region defined not by sharp edges, but by the reach of its gravitational influence. Beyond that, the gravity of other clusters and groups begins to dominate. Within the local group, most of the galaxies are small dwarf systems. Many of them orbit the Milky Way or Andromeda, while a few drift freely in between. These dwarfs are faint and diffuse, some containing only a few 100,000 stars. They represent the smallest scale of galactic structure, fragile systems easily disturbed by the gravity of larger neighbours. Despite their size, they play an important role in the evolution of galaxies, supplying fresh material through mergers and interactions. Each galaxy in the local group moves in response to the combined gravity of the others. Their paths form a complex web of motion, the Milky Way and Andromeda moving toward each other, smaller galaxies spiralling around them, and the entire group drifting as a whole toward a larger cluster known as Virgo. The local group's centre of mass lies somewhere in the empty space between the Milky Way and Andromeda, though neither occupies that exact centre. They orbit each other in a slow, mutual fall, like two skaters spiralling closer on a frozen lake. The smaller galaxies trace looping paths around them, bound by the same gravitational field but following their own intricate trajectories. One of the remarkable things about this arrangement is how stable it is over time. Despite the motion, the distances between galaxies change slowly. Gravity binds them, but it also balances them. The local group has existed for billions of years and will continue for billions more. Over time, some of its smallest members may be absorbed, others may drift away. But the core relationship between the Milky Way and Andromeda will define its structure for most of its remaining life. Their eventual merger will mark the next stage in its evolution, turning the local group into a single massive galaxy surrounded by a halo of remnants. Beyond our immediate neighbourhood, the local group is part of a larger assembly called the local sheet, a flattened structure containing several nearby groups of galaxies. These groups in turn are part of the Virgo supercluster, a vast collection of thousands of galaxies spread across more than 100 million light-years. And even that supercluster is only a part of an even larger pattern, a filament of the cosmic web connecting to other clusters and voids. The local group, for all its richness, is only one small knot in a structure that extends beyond anything we can directly observe. Understanding our relationship with our galactic neighbours helps place the Milky Way in context. It reminds us that galaxies are not static islands, but parts of a network, interacting and evolving together. The exchange of matter between them, through gravitational encounters and streams of gas, contributes to the ongoing cycle of creation. When two galaxies pass close enough, their gravity can draw out long tails of stars and gas, forming new structures between them. These interactions can ignite bursts of star formation, lighting up regions that were previously quiet. In this way, the local group is not just a cluster of galaxies but a dynamic system, alive with motion and change on cosmic timescales. When astronomers observe the local group in detail, they see history written across it. Streams of stars trace the remnants of past mergers. Clouds of hydrogen connect one galaxy to another. The orbits of satellites reveal patterns of past encounters. Each piece tells part of the story of how the group formed and evolved. The Milky Way and Andromeda likely began as separate condensations of gas within the same larger region of matter billions of years ago. As they grew by drawing in surrounding material, they became the dominant members of their region, gradually capturing smaller galaxies into orbit. Their motions through space reflect that shared origin, a slow mutual attraction shaped by the same gravitational currents that built the universe itself. When we look at the night sky, most of the stars we see belong to the Milky Way, but a few of the faint patches and smudges are distant galaxies within the local group. The Andromeda Galaxy, visible even without a telescope, is the most prominent. The Magellanic Clouds, visible from southern latitudes, are closer companions. The Triangulum Galaxy, another member of the group, lies near Andromeda and is thought to interact with it gravitationally. Together, these visible neighbours give us a glimpse of our local cosmic environment, a small sampling of the billions of galaxies that fill the universe. Even though the distances between these galaxies are enormous, they're still relatively close compared to the spaces between galaxy clusters. Within the local group, gravitational attraction dominates, keeping the members bound together despite the expansion of the universe. Beyond its borders, that expansion takes over, carrying galaxies farther apart. This balance between local gravity and cosmic expansion defines the structure of the universe. Clusters and groups bound eternally, drifting apart from one another across the vast, stretching fabric of space. The local group is one of countless such islands in an ocean of expansion, each containing its own history of formation and motion. It's fascinating to think that our entire galaxy, with all its stars and planets, is just one member of this community. The Milky Way's spiral arms, the Sun's orbit, the solar system itself, all are moving as part of a larger system of galaxies, bound together by the same gravity that holds planets around stars. The scale changes, but the principle remains the same. The local group is a galaxy-scale version of the solar system, and the Virgo supercluster is a larger version still. The same laws apply everywhere, repeated endlessly at different scales, forming a pattern of motion that fills the universe. If we could somehow view the local group from a distant vantage point, we'd see two great spirals, the Milky Way and Andromeda, slowly approaching, surrounded by dozens of smaller companions. The smaller galaxies would look like faint specks scattered around them, some in close orbits, others stretched into streams by gravity. The whole system would be drifting through space as one entity, turning imperceptibly as it moves. From that distance, it would look serene, a quiet collection of galaxies floating together, their light blending softly into the background glow of the universe. And within that scene, our own position would be almost invisible. The sun's light would vanish into the brightness of the Milky Way's spiral arm. Earth would be smaller than dust in the context of that scale. Yet everything that we know, every history, every thought, would be contained in that tiny part of one galaxy, moving as part of the same gravitational network as the rest. To know that is not to feel small, but to feel connected. The local group isn't just our neighbourhood in space, it's part of the framework that gives the universe its structure. The quiet motion of these galaxies, the long orbits and slow interactions, form the background rhythm of cosmic time. The Milky Way and Andromeda draw closer each year. The smaller galaxies drift and merge, and the entire group continues its drift through the universe, carried by forces that began with the birth of everything. Nothing in this system is static. Even the space between galaxies changes, expanding and stretching as the universe evolves. Our local group moves with that flow, balanced between internal gravity and the outward expansion of space. A small, coherent cluster of light drifting through the darkness, surrounded by the quiet hum of the cosmos continuing without pause. When we talk about the universe, there's a point beyond which we can't see. It isn't a wall, and it isn't a place where things stop existing. It's simply the limit of what light has had time to reach us since the universe began. That limit is called the observable horizon, or the observable universe. It defines the farthest distance from which any information can ever reach us, because light travels at a finite speed and time itself has a finite age. Beyond that horizon, there are regions we'll never see, not because they're hidden by matter or shadow, but because their light has not yet arrived, and in many cases never will. To understand this boundary, you have to think about the age of the universe itself. The best evidence suggests that the universe began about 13.8 billion years ago, in a hot, dense state that has been expanding ever since. You might expect that this would mean the observable universe is about 13.8 billion light-years across, since that's how far light could have travelled in that time. But it's much larger than that, because the space through which that light has travelled has expanded while the light was on its way. As a result, the region from which the oldest light can reach us today is now about 46 billion light-years away in every direction. That means the observable universe forms a sphere roughly 92 billion light-years across, an immense region, but still only a portion of the whole. When you look at the night sky, every photon that reaches your eyes has travelled through time and distance to get here. The farther away its source, the older that light is. Some of the stars we see are tens or hundreds of light-years away. The light from distant galaxies can be millions or billions of years old. The most distant light of all, the faint uniform glow that fills the sky in every direction, comes from a time when the universe was only about 380,000 years old. That light is known as the cosmic microwave background. It's the afterglow of the early universe, the leftover radiation from when the first atoms formed and light could finally travel freely through space. Before that moment, the universe was opaque. It was filled with a hot plasma of protons, electrons, and photons constantly interacting. Light couldn't move freely because it was constantly scattered by charged particles. As the universe expanded and cooled, those particles combined to form neutral atoms, allowing photons to travel unimpeded for the first time. The light released at that moment has been travelling ever since, stretched by the expansion of space into microwave wavelengths. When we detect it today, we're seeing a snapshot of the universe as it was nearly 14 billion years ago, a faint echo from the time when the first transparent space appeared. That light defines our cosmic horizon. Beyond it, there's more universe, but we can't observe it directly. The regions beyond the observable limit are not different in kind. They're just farther away. The same laws of physics apply and the same structures likely exist, but their light hasn't reached us yet. The horizon isn't a physical edge. It's more like the boundary of a growing bubble of visibility, expanding as time passes. Each year, light from slightly farther regions arrives, and our observable universe grows larger. But the expansion of space also carries distant galaxies away from us faster than light can travel. So beyond a certain point, even light emitted now will never catch up. Those regions are permanently beyond reach, moving away faster than time can bridge. This expanding boundary creates an interesting paradox. The universe as a whole may be infinite, but we can only see a finite part of it. What lies beyond the observable horizon is not darkness, but more of the same. More galaxies, more clusters, more structures continuing endlessly. If the universe is truly infinite, then what we observe is just a small patch of it, a fraction of an unbounded whole. If it's finite but unbounded, like the surface of a sphere, then travelling far enough in one direction might eventually bring you back to where you started, though space is expanding too fast for that ever to happen in practice. Either way, our visible universe is a window, not a container. The idea that there's a limit to what we can observe isn't new. Even in ancient times, people wondered how far the stars extended. But the modern concept of the observable universe adds a layer of physical meaning to that intuition. It's not limited by the sensitivity of our instruments, but by the nature of time and light. No telescope, no matter how powerful, can see beyond it, because there simply hasn't been enough time for light from those regions to reach us. The horizon defines what's physically knowable. Beyond it, everything remains hidden behind the curtain of cosmic time. When astronomers look toward the edge of the observable universe, they see galaxies as they were billions of years ago. Because light takes time to travel, the deeper we look into space, the further back in time we see. This creates a kind of natural time machine. The most distant galaxies we can observe are seen as they existed when the universe was only a few 100 million years old. They appear faint, red, and small, because their light has been stretched and dimmed by the expansion of space. Some of those early galaxies no longer exist in the form we see them. They've merged, evolved, or vanished entirely, but the light they emitted long ago is still on its way to us. The cosmic horizon also helps define what we mean by now in cosmology. Because light from distant objects takes so long to reach us, our view of the universe is always out of sync. We see nearby stars as they were years ago, and distant galaxies as they were billions of years ago. There is no universal present that applies everywhere at once. Time flows locally, but across cosmic distances it becomes fragmented. The universe we see is a mosaic of different eras layered together, each piece arriving at our eyes at a different moment. The horizon marks the oldest layer we can access, the farthest past that can still send light our way. When scientists map the universe within that horizon, they find that galaxies aren't evenly distributed. They form filaments and walls separated by enormous voids. This large-scale structure, called the cosmic web, extends as far as we can see. It's the skeleton of the universe, shaped by gravity acting on matter over billions of years. Closer to us, we see clusters like Virgo and Laniakea, vast groupings of galaxies connected by thin threads of light. Farther out, those threads fade into the background of ancient radiation. The pattern seems to continue indefinitely, suggesting that the same kind of structure repeats beyond our observational limits. The observable horizon isn't static. As time passes, the universe expands, and light from more distant regions reaches us. In that sense, our visible universe grows. But expansion also means that distant galaxies are moving away faster over time. Some of them have already crossed what's called the cosmic event horizon, the distance beyond which their light will never reach us, even in the infinite future. The event horizon marks the ultimate boundary of visibility, the line beyond which everything recedes faster than light because of the stretching of space itself. Galaxies that cross that threshold are effectively gone from our view forever. Their light already in transit will still arrive, but anything they emit afterward will never reach us. In the far future, as billions of years pass, this will have profound effects on what remains visible. The expansion of the universe is accelerating due to dark energy, a mysterious form of energy that permeates space and drives its expansion faster over time. Because of this acceleration, distant galaxies will gradually slip beyond the event horizon. Eventually, only the nearest group of galaxies, our local group, which includes the Milky Way and Andromeda, will remain gravitationally bound and visible. All others will fade beyond sight, their light redshifted until it disappears. For future observers living trillions of years from now, the universe will appear dark and empty, with only their local galaxies remaining. The cosmic horizon will have closed around them, leaving the wider universe hidden beyond reach. Even today, the light from the most distant galaxies we see has been stretched to infrared and radio wavelengths. Telescopes like the James Webb Space Telescope are designed to detect this faint, red-shifted glow, revealing galaxies that formed in the first few 100 million years after the Big Bang. Observing them is like looking through layers of time, each more distant object revealing an earlier chapter of the universe's history. Through such observations, astronomers can reconstruct how galaxies formed, how stars first ignited, and how structure emerged from the nearly uniform background of the early cosmos. The cosmic microwave background sits beyond all those galaxies, marking the limit of transparency. It's the oldest light we can see, and its uniformity reveals the smoothness of the early universe. Tiny variations in its temperature, differences of only a few millionths of a degree, correspond to the seeds of structure that would later grow into galaxies and clusters. By mapping those variations, scientists can infer the conditions of the early universe and the amount of matter, energy, and curvature it contained. The horizon defined by this light isn't just a distance, it's a record of the universe's birth and its gradual evolution into what we see today. The idea that there's a boundary to what we can observe doesn't mean there's a boundary to existence. The universe beyond the observable horizon continues indefinitely, following the same physical laws. In fact, some cosmological models suggest that what lies beyond might be nearly identical to what we see here. More galaxies, more stars, more matter spread across infinite space. Others propose that conditions could vary, with different regions having different densities or even different physical constants. Because we can never receive light from those regions, we can't know for sure. Our horizon defines the edge of empirical knowledge, the line between observation and speculation. In a way, the observable universe is like a personal horizon for humanity. It represents everything we can see, measure, and understand. Beyond it, we can only imagine. It's a reminder that knowledge, no matter how vast, is always partial. The light we study, the galaxies we map, the background radiation we detect, all of it comes from within that bubble of visibility. Outside it, the cosmos continues, silent and unreachable, carrying on its processes without our witness. Yet even within this limit, the amount of information available is immense. Every photon, every signal, every faint glimmer of light carries a piece of the universe's history, waiting to be read. The existence of this horizon also gives a sense of time's direction. Light that reaches us now was emitted long ago, and light we emit now will travel outward, perhaps reaching distant observers billions of years in the future. In that sense, horizons work both ways. We're at the center of our own observable universe, just as every observer anywhere else is at the center of theirs. Each horizon is personal, defined by time and light, yet overlapping with others. The universe doesn't have one single center. It has as many centers as there are observers, each surrounded by a sphere of visibility expanding at the speed of light. If you think about it carefully, the concept of an observable horizon doesn't make the universe feel smaller. It makes it feel more alive. It shows that space and time are connected, that our view of reality changes with the passage of time. What we can see today is more than what we could see 1 billion years ago, and less than what we'll see 1 billion years from now. The edge of the visible universe keeps moving outward, revealing more of the cosmos as time allows. Each photon that arrives adds a little more detail to the picture, a little more clarity to the story of how everything began. Even though the horizon represents a limit, it's also a frontier. Every advance in technology pushes that frontier slightly farther. New telescopes, new detectors, and new ways of analyzing light allow us to see galaxies that were previously invisible. Each discovery takes us closer to the beginning of time, to the point where light and matter first separated. We'll never reach the end of what can be known, but we can keep moving toward it, step by step, observation by observation, photon by photon. When you look at the sky, the light that reaches you is a message from within that horizon, a record of the universe unfolding across billions of years, the faintest glow, the most distant galaxy, the subtle warmth of the cosmic background. All of it carries information about time, distance, and change. The observable horizon is not the end of the universe, it's the edge of what we can see, the limit imposed by the speed of light and the age of everything. Beyond it lies more of the same vastness, stretching endlessly, waiting silently for light that will never arrive. And yet, even within this boundary, the universe remains immense enough to defy exhaustion, a boundless expanse continuing far beyond what sight or even imagination can reach. When you start to grasp the scale of the universe, it's natural to feel small. The numbers are so far beyond human comprehension that even describing them becomes a kind of surrender. Billions of stars, trillions of galaxies, distances measured in light years and ages measured in billions of years, it's too large to hold in the mind at once. The temptation is to see our place in all this as insignificant, to imagine that a single planet orbiting an average star must barely matter in such a vast cosmos. And yet that reaction, while understandable, misses something essential. Being small doesn't mean being meaningless. In a universe this large, smallness is not a flaw. It's a feature, one that reveals how scale and perspective give everything its place. Every structure in the universe exists within something larger. Planets orbit stars, stars gather into galaxies, galaxies cluster into superclusters, Those clusters thread together into filaments stretching across cosmic space. Each level of structure emerges from the interactions of smaller parts, and each depends on the stability of those parts to exist. Small things are not separate from the large, they make the large possible. The orbit of a single planet may seem unimportant in the context of a galaxy, but it's part of the same system of gravity that shapes the whole. The same laws that govern galaxies also govern the movement of atoms. The universe is consistent across scales. From a human perspective, that consistency gives meaning to our size. Our bodies, made of ordinary matter, are built from atoms forged in the cores of stars. Those atoms follow the same physical rules that shape galaxies and stars themselves. The gravity that holds planets in orbit also holds us to the ground. The chemical reactions that sustain life are the same types of processes that power the stars, only occurring at different energies and scales. The small and the large are not opposites. They're reflections of the same structure operating across different magnitudes. When you understand that, smallness becomes a way of belonging. It's easy to forget how much complexity small scales contain. A single cell in the human body contains billions of molecules arranged with precision, interacting in networks of chemistry that we still don't fully understand. The structure of DNA, just a few nanometers across, encodes the instructions for an entire organism. At the atomic level, empty space dominates. The nucleus of an atom is tiny compared to its overall size, and yet nearly all its mass resides there. The pattern repeats at every level. Emptiness containing structure, structure containing motion, motion producing order. The same pattern that makes galaxies form from clouds of gas also makes atoms form from subatomic particles. Scale changes, but the underlying logic stays the same. If you could shrink yourself to the size of a molecule, you'd find that the space inside matter feels as vast as the space between stars. Atoms are mostly empty, their electrons orbiting far from their nuclei relative to their size. The universe, viewed at any scale, is full of gaps that allow movement and interaction. That emptiness is what makes complexity possible. Without space between things, there would be no motion, no change, no life. Smallness is what allows room for relationships, between atoms, between planets, between galaxies. Everything exists in connection with something else, and those connections are what give shape to the universe. From our position on Earth, it can seem that the scale of the cosmos dwarfs us beyond significance. But that feeling comes from measuring ourselves by the wrong standard. Meaning doesn't depend on size. The human brain, small enough to fit in your hands, is capable of conceiving the scale of the universe. Within its network of neurons, patterns of electricity and chemistry create awareness that can contemplate galaxies billions of light years away. The fact that a system of molecules and cells can imagine the structure of the cosmos that gave rise to it is not a contradiction. It's evidence of connection. The universe has produced something within itself capable of seeing itself. Smallness, in that sense, is not weakness, but precision. The fine resolution of consciousness emerging from vastness. Even the planet we live on, small compared to the galaxy, is large enough to sustain a world of infinite variation. Mountains, oceans, clouds, and forests, all of it depends on the thin shell of matter and energy that surrounds a single star. When you zoom out, Earth becomes a point of light, but when you zoom in, that point contains the entire history of life, from simple bacteria to thinking beings. Scale determines perspective, and perspective determines what seems important. The universe looks different depending on where you stand, and every point of view reveals something true. The vast and the tiny are not competing realities, they're complementary descriptions of the same whole. When astronomers study the universe, they rely on the small to understand the large. The faint flicker of light from a distant galaxy contains clues about its motion, age, and composition. The tiny shift in wavelength caused by redshift tells us how fast it's moving away. The smallest deviations in the cosmic microwave background reveal the initial fluctuations that led to the formation of galaxies. The smallest measurable quantities lead to the largest insights. Scale is not a hierarchy of importance, but a continuum of detail. Each level provides a different way of reading the same story. If you were to look at the Earth from another star system, you'd see a faint dot orbiting an average star. There would be nothing outwardly remarkable about it, and yet, within that dot are oceans, weather and life. That same planet, invisible from nearly everywhere else in the galaxy, is the only place we know where the universe looks back at itself through conscious beings. In that context, smallness becomes significance of a different kind, not the importance of size, but the importance of awareness. The ability to observe, to think, to wonder, is not separate from the cosmos, but an expression of it. We're not outside observers, we're part of the system, participating in its unfolding. When you think about the observable universe, 92 billion light-years across, and then compare that to the scale of the human body, the difference is unimaginable. And yet, both scales coexist without conflict. The same constants of nature that govern the expansion of space also govern the interactions of molecules in your cells. Light, gravity, and quantum mechanics operate everywhere, across all distances. There is no size too large or too small for physics to reach. The consistency of those laws means that every structure, from the smallest particle to the largest cluster, is part of one continuous framework. The sense of disconnection we feel is only a matter of perception. Our smallness gives us the ability to measure, to compare and to understand. It allows us to exist in a region of the universe where conditions are stable enough for life but complex enough for consciousness. If we were larger, made of stars or galaxies, we couldn't think or observe. The processes that produce life depend on scales, where matter can form molecules, where temperature and pressure can support chemistry, where time passes slowly enough for evolution to take place. The scale of our existence is precisely tuned to the conditions that allow awareness to emerge. Smallness in this sense isn't a limitation, it's the necessary condition for being able to see it all. When scientists look for life elsewhere in the universe, they search for planets of similar scale to ours, worlds where liquid water can exist, where atmospheres can form, where energy from a star can drive cycles of chemistry. These requirements aren't arbitrary, they're shaped by the physics of size. A planet too small can't hold its atmosphere, one too large becomes a gas giant. Between those extremes lies the narrow band where complexity can arise. Our small planet exists in that balance, its scale perfectly suited to the processes that sustain it. The universe doesn't privilege large things over small ones. It allows both, each fulfilling a role in the larger structure. The power of smallness also appears in time. Human lifespans are brief compared to the age of the cosmos, yet that brevity allows awareness to renew itself across generations. The timescale of a single life fits within the flow of evolution, technology, and knowledge. We don't need billions of years to understand the universe. We only need enough time to observe and think. The shortness of our existence gives urgency to curiosity, driving us to explore. In the context of cosmic time, that curiosity is itself extraordinary, a fleeting phenomenon that still manages to reach across billions of light years through observation and inference. Smallness has another kind of power, the ability to hold detail. Large systems reveal patterns, but small systems reveal texture. A galaxy shows the distribution of stars, a planet shows the conditions for life. Within that life, a single organism shows the complexity of biology. Within that organism, a single cell shows the precision of chemistry. The deeper you look, the more you find. Smallness concentrates meaning rather than diluting it. The closer you examine anything, a leaf, a crystal, a strand of hair, the more structure and process you discover. Scale doesn't erase significance, it multiplies it. When we think about the Milky Way, we see ourselves as tiny compared to its hundreds of billions of stars. But every one of those stars is small compared to the galaxy as a whole. The galaxy in turn is small compared to the cluster it inhabits, and that cluster is small compared to the cosmic web. Smallness is relative. It depends on what you're comparing to. From the perspective of a molecule, a human being is vast. From the perspective of a galaxy, a human being is invisible. Both perspectives are valid, but neither captures the full picture. The universe contains all scales at once, each nested within the other. There's also something grounding in recognizing that smallness brings stability. Large systems can collapse under their own gravity, or tear themselves apart through violent processes. Small systems can persist quietly for long periods, maintaining balance through subtle interactions. The stability of atoms, molecules, and biological systems depends on the precision of small forces, electromagnetic bonds, quantum energy levels, chemical equilibria. Those details sustain life and matter. Without them, the large structures we admire, stars, galaxies, and planets, couldn't exist in their current form. From a certain perspective, smallness allows intimacy. We can interact with our surroundings directly, experience them through touch, sound, and sight. The scale of our senses matches the scale of the world we inhabit. We can hold a rock, taste water, feel warmth from sunlight. These are local experiences rooted in smallness. The large-scale structure of the universe doesn't offer experiences like that. It offers context. The small scale offers connection. Both are necessary. The cosmos gives us the setting. Our size gives us the ability to notice it. Even in the context of the observable universe, where distances stretch for billions of light years, the act of noticing has weight. Every measurement, every observation, every question extends the reach of awareness by a tiny amount. Each step in understanding builds on countless others. Science itself is a collective expression of smallness, individual efforts combining across time to form knowledge large enough to describe galaxies and small enough to explain atoms. The human scale allows for both, connecting the details of the microscopic with the immensity of the cosmic. When you think about the contrast between our size and the scale of the universe, it's tempting to focus on what we can't do, how far we can't travel, how long we can't live, how much we can't see. But there's another way to look at it. Our limits are what make perspective possible. If we were infinite, there would be nothing to measure, no outside to compare against, no sense of wonder. Smallness defines contrast, and contrast creates meaning. Without it, even infinity would be invisible. The awareness of scale is what makes consciousness remarkable. To exist as something small within something vast, and to be able to perceive that relationship is unique. No galaxy or star can reflect on its size, no planet can measure its distance to another, but life can. Through life, the universe becomes aware of its own scale. Smallness gives rise to that possibility. It's not a disadvantage, it's the bridge between knowledge and existence. The fact that we can feel small at all means that we can also understand. So when you look up at the night sky and feel the weight of its distance, remember that your ability to feel that at all is part of what connects you to it. The galaxies, the stars, the spaces between, all of it exists beyond measure, but your perception of it completes the picture. The power of smallness is the power to notice, to wonder, to describe. It's the way the universe makes sense of itself, one small awareness at a time, within the immeasurable expanse that continues, quietly, far beyond our reach. Every time you look up at the night sky, the Milky Way appears as a soft band of light, stretching across the darkness like a pale bridge. What you're really seeing is the combined glow of billions of stars, each one a distant sun, each one part of a pattern so vast that the human mind can only touch it in pieces. The galaxy isn't just out there far away, it's around you, behind you, beneath you. Every direction you turn, every patch of space, Every bit of darkness is part of it. The Earth orbits within one of its spiral arms, the Sun moves with it, and you, sitting here, are carried along inside it without effort or awareness. The Milky Way isn't a picture you're looking at, it's a place you're inside. Thinking about that can create a strange balance between scale and familiarity. You're small compared to the galaxy, but you're not separate from it. The matter in your body, the atoms in your blood, your bones, your brain, all came from stars that lived and died long before the Sun was born. You're made of recycled material, built from elements that were once parts of other worlds. The calcium in your bones was forged in the heart of a massive star. The iron in your blood came from the debris of a supernova. The oxygen you breathe was made by generations of stars fusing lighter elements into heavier ones. You are, in the most literal sense, the product of galactic history. When you breathe, the molecules entering your lungs are part of an ongoing exchange that has lasted for billions of years. Atoms once bound in stone or water move through the air, through living things, through time. Every living being participates in that cycle. The Milky Way provides the materials, and life rearranges them into temporary patterns. Even thought itself, the electrical signals travelling through your brain, is made possible by the properties of those same elements. Sodium, potassium, carbon, oxygen, products of the galaxy's chemistry, combine to create awareness. In that sense, your mind is part of the galaxy's structure, one of its countless expressions. If you think of the Milky Way as a vast ecosystem, it's one that operates on scales far beyond ordinary perception. Stars are born in cold clouds of gas, live for millions or billions of years, and then die, returning their materials to space. The cycle repeats endlessly, each generation enriching the next. That process has been going on since the galaxy formed more than 10 billion years ago. Our solar system joined late in the story, formed from the remains of many earlier generations of stars. The fact that life exists here is part of that continuity, an outcome of the galaxy's long history of transformation. Every living thing, every thought and breath, is a temporary arrangement of matter within that ongoing process. From the human perspective, the galaxy moves slowly, its rotation taking hundreds of millions of years. But if you could see time sped up, you'd watch its arms turn like currents in a vast ocean. Clouds of gas would collapse into clusters of stars, and those stars would drift apart, spreading their light across the disk. Supernovae would flash and fade like sparks, scattering new elements into the surrounding medium. Over eons, the spiral arms would shift, stretch, and renew themselves, never still but always balanced. The entire structure would appear to breathe, expanding and contracting in the rhythm of cosmic motion. From that view, every atom that makes up your body would pass through countless configurations, joining and separating again, part of an unbroken exchange of energy and matter. It's remarkable to think that the same physical processes shaping the Milky Way also shape your thoughts. Gravity, electromagnetism, nuclear forces, these are the same interactions at work in the stars and in the molecules of your brain. The galaxy isn't distant from you in principle, only in scale. The physics that governs its rotation also governs your heartbeat. The light that travels from its stars obeys the same laws as the light entering your eyes. You're not an observer standing apart from the galaxy. You're an instance of it, a localized concentration of its materials briefly arranged in a way that can reflect, reason, and remember. When you look at the night sky, what you're really doing is allowing the galaxy to see itself. The light from distant stars enters your eyes, triggers chemical reactions in the cells of your retina, and creates signals that your brain interprets as sight. In that moment, light that has travelled for thousands of years becomes part of your awareness. The act of seeing is a kind of participation. The galaxy produces the light, and you, made from its matter, are the receiver. Observation and existence merge into the same process, energy changing form, one system recognizing another. The human mind evolved on a small planet, under a narrow band of sky. For most of history, the Milky Way was simply a familiar feature of that sky, a river of pale light with no known source. Only recently have we begun to understand what it truly is, not a cloud or a band of mist, but the cross-section of our own galaxy seen from within. Every improvement in our ability to measure and observe has expanded that understanding. The telescope turned a blur into a multitude of stars. Photography revealed their arrangement. Radio, infrared, and X-ray instruments showed the hidden structure of gas, dust, and energy. Bit by bit, the picture grew, and with it, our sense of place. That growth in understanding didn't make the galaxy smaller. It made our sense of belonging larger. To know that we orbit within one arm of a spiral galaxy, midway between the center and the edge, is to locate ourselves within a living structure. A structure with a history and a future, one that changes over time but endures on scales we can barely imagine. That knowledge doesn't reduce mystery, it deepens it. The more we learn, the more we recognize that we are surrounded by processes so vast and slow that they appear timeless. And yet, those same processes are made of the same materials and governed by the same rules that operate here and now. You can think of your mind as a microcosm of that structure. Billions of neurons connect in intricate networks, each one carrying electrical impulses across tiny gaps. The number of possible connections and patterns within the brain exceeds the number of stars in the galaxy. The mind contains its own kind of vastness, not measured in distance, but in complexity. Thoughts form, move, and fade like stars in miniature, each one influencing the next. The activity of the brain, though it happens on microscopic scales, mirrors the dynamics of the cosmos in its interconnection and constant change. The patterns of firing neurons resemble the branching filaments of galaxies, not because they share a physical connection, but because complexity itself tends to form similar shapes. In that sense, there really is a galaxy in your mind. Not a literal map of stars, but a structure of patterns and relationships shaped by the same principles. The brain doesn't contain the universe, but it reflects its logic. Structure arising from simplicity, order from motion, consciousness from matter. When you think about the Milky Way, you're not reaching outward into something foreign. You're extending inward toward the same principles that built both stars and thought. The difference between you and the galaxy is only one of scale. Both are systems of energy and matter that change over time, both follow physical laws, and both contain complexity that emerges naturally from those laws. Understanding that doesn't take away the sense of awe, it deepens it. To know that your awareness is a small part of a much larger process doesn't make it less remarkable. It means that the galaxy isn't just something to look at. It's something you participate in. Every action, every thought, every breath is part of the ongoing motion of matter that has been moving since the beginning of time. The boundaries between your body and the universe are temporary. The molecules that make up your cells were once part of stars and will one day return to them. You are part of a cycle that began long before you and will continue long after. The galaxy is not distant. It's continuous with you. When you picture the Milky Way from the outside, the spiral arms, the glowing core, the halo of stars, you're imagining a structure built over billions of years by simple forces acting on immense scales. That structure doesn't exist in isolation. It's part of a larger network of galaxies, each one connected through gravity to others, forming a web that stretches across the observable universe. The same patterns of clustering that exist among galaxies exist among neurons, cities, ecosystems. The universe builds structure by repeating the same logic at different scales. Complexity is not an exception. It's the natural result of time and interaction. The light from the stars in the Milky Way moves constantly through space, and much of it will never be seen. It will travel in every direction, crossing empty distances, absorbed by dust or bent by gravity. Some of it will reach planets, some will fade into the background. But the process continues, endlessly, with new stars forming and new light taking its place. The galaxy's energy circulates through this exchange. Light, matter, gravity, motion, a continuous transfer that sustains its form. In a smaller, faster way, the human body does the same. Energy flows through it, maintaining order while everything within it changes. Life is a form of organized motion, built on the same physical principles that sustain galaxies. To think about the galaxy in these terms is to see connection instead of distance. The stars above are not separate points scattered across emptiness. They're part of a structure that you're inside of, and the materials that form them are the same materials that form you. The distinction between the observer and the observed is only a matter of arrangement. The galaxy is not something external to your existence. It's the environment that makes existence possible. The act of reflection, sitting quietly, thinking about your place in the Milky Way, is itself an expression of cosmic continuity. You're a pattern of matter capable of understanding other patterns. The awareness you carry is made possible by the same physics that holds galaxies together. It's not symbolic, it's literal. When you think about the universe is thinking about itself through you. That doesn't require mysticism or metaphor. It's simply the natural consequence of matter that has evolved to become aware. Even if that awareness lasts only a brief moment on the cosmic timescale, it's still part of the galaxy's story. The lifespan of a human being is short compared to the age of stars, but time doesn't measure significance. Duration isn't the same as meaning. A supernova lasts only seconds, yet it reshapes everything around it. The briefest moment of consciousness is still a real part of the universe's process, one that links the microscopic and the cosmic, the immediate and the infinite. As you sit beneath the night sky, you're sharing motion with everything you can see. The Earth turns, carrying you eastward. The planet orbits the sun. The sun moves around the center of the galaxy. The galaxy drifts with others through the expanding fabric of the universe. You are in motion at every level, and yet it feels still, because you are moving with it. That stillness within motion is the essence of belonging. It's not something you have to earn or discover. It's the condition of being alive in a universe that is both larger and more continuous than anything we can imagine. If you could somehow compress all that knowledge, the structure of galaxies, the scale of time, the chemistry of life, into a single thought, it might sound like this. You are part of the Milky Way, and the Milky Way is part of you. Every atom, every signal, every motion connects. There is no line that separates you from the galaxy, except the one drawn by perception. When you close your eyes, the light from those distant stars still reaches you. It moves through the atmosphere, through space, through time, and lands softly on your skin. The galaxy surrounds you, not as something to reach for, but as something you already inhabit completely. And while your mind can't hold all of it at once, it doesn't have to. The awareness of it, the steady realization that you are inside something so vast and continuous, is enough. The Milky Way moves, and you move with it. The stars burn, and their light becomes part of your vision. The matter that once formed stars now forms thoughts. The galaxy exists outside you, and within you, in patterns of light, matter, and understanding that mirror each other perfectly. The night sky is quiet, but the quiet isn't empty. It's the soundless background of motion, the steady continuation of processes that began long before life existed. You don't need to hear it to be part of it. Every heartbeat, every breath, every thought is already synchronized with that motion. The galaxy isn't above you, it's within you, in every atom, in every spark of energy, in every moment of awareness that connects one scale of the universe to another. The Milky Way turns, and so do you. Endlessly, both part of the same long ongoing motion that fills the cosmos with light.